Hello everyone, I'm Yaowen Zhang from National Innovation Institute of Defense Technology in China, and it is my pleasure to introduce my job. The title I'm going to talk about is Networked Multi-Robot Collaboration in Cooperative and Competitive Scenarios and Communication under Communication Interference. As we all know, in a large area scenario, multi-robot system can improve the execution efficiency of tasks, especially collaboration in complex environments. Multi-robots collaboration often relies on information sharing, in particular in the case of active signal jamming. Communication connectivity will face challenges. Secondly, the training data and models are crucial in applying AI algorithms. How we can make sure to always catch the correct information and modify the model based on the local variation trains is another challenge. In this paper, we consider a scenario where a team of predator robots collaborative survey an area for preventing the invasion from opponent robots. In this scenario, the predator can share the sensing information of prey robots. In order to constrain the surveillance performance, some interfering robots are added. It could break the communication connectivity between predators. This is a typical cooperative and competitive decision problem involving multiple optimization variables from electromagnetic and geographic domains. An intuitive way, a multi-robot system behavior model is to predefine the action rules for each robot. However, enumeration of entire situation is difficult. In this paper, we selected referencement learning to solve it. Its main advantage is that the agent can interaction with environment and learning optimize the model with multitask. It is widely used to solve decision problems in multi-agent system. First of all, we simplify the scenario as shown, and we model the perception and communication of robots. Then describe the problem with the constraints as a Markov decision process. With the limit of perception and communication model, we implement the deep first search to dynamic grouping to maximize the observation scope. For second problem, training data modify, we propose a method named scenario curriculum learning. We set two lists of task decomposition to verify the effect of this method. In this multi-domain environment, it contains geographical obstacle. It can interference action space and break communication. Our main purpose is to train cooperative strategies of predators. So we consider that prey robot as a moving target, which has global observation scope. In addition, interfering robots can disturb the communication lines between predators. About predators' robots, it states as shown, such as if a predator has perceived a prey robot, it will pursue the prey robot. And if a predator has perceived another predator, its teammate, they will interconnect as a formation. If a predator perceives nothing or disconnects with teammates under the jamming signal, it will patrol in an assigned area. Meanwhile, a predator can reconnect interfering the predator to reformation. In reinforcement learning, we can define the reward function upon different states. The definitions as shown. We simplify the communication and the perception range as round with different radii. In reality, the sensing radius is usually larger than communications. Robots in the scope of interconnection constitute the Unicom group. Perception range can be extended through interactive robots in group. In order to maintain connectivity under the jamming signal, predators adopt two modes. Conventional communication, it has lower power for energy saving, and strong communication, it has higher power and strong directivity, consumes more energy, and resists interference to a certain extent. The two modes have different radii. Interfering robot has a circular interference area. Model selection according to the relationship of distance between the current predator and its the nearest collaborative teammate. For ensuring a center energy consumption, the strong communication mode with higher power consumption has a smaller radius than the conventional mode, such as RH is less than RL. And in this figure, robots in the Unicom group can share information by maximize the perception range. For current agent I, there is a set of list G. For example, agent 1 searches the nearest agent to connect, such as agent 2 and agent 4, and add them into the set G. Then we chose the agent 2 in the set G and search the nearest agent is agent 4, but agent 4 is already in the set. And next, continue searching according to the agent 4 in the set G and agent 3 and put it into the set G. One by one, at the end, we have two group lists. The list of agent 1, 2, 3, 4, 5 and the list of agent 6, 7. We selected the referencement learning framework for training mentioned scenario. Each agent has actor and critic network as shown. Actor network is used to generate actions according to the state, and the critic network evaluates the joint behavior output computed upon the state. A reply buffer pool D is mini-bench for the collecting experiments of trumps. In the training process, the input state vector about agent is in the same communication group G, and the critic network calculated the Q function of state action pair. After collaboration model training, we consider the model modify problem. We propose scenario curriculum learning. Consider about multitask networked multi-robot system in multi-domain. For dynamic interact process and non-spare reward are constant. Direction of learning are easily to fall into local optimum, and computing cost will increase correspondingly in the face of large-scale system. In the background of above problem, scenario decomposition of ICL as shown. In scenario 1, all agent has group observation, and in the scenario 2, all agent has partial observation, and the reward need consider about adding formation reward atom. In the scenario 3, we introduce interfering robot and the predator must switch communication mode under the jamming. And the final scenario, all agents should be trained with avoiding geographical obstacle. The priority of the task should be first, it should be trained with pursuit, and second, it should be trained with formation, and next, it should be trained with partial, and last, it should be trained with avoidance. In simulation, the first result shown that reference learning could obtain effective collaborative strategies. Moreover, the algorithm BiC-DDPG has advantage models from cross-cooperation experiments. The rightmost in the first figure and the reward indication in the second figure. As simulation presented in the right result, the red ball represents predator robots, and their size indicates the effective attack range. And green balls represent the opponent robots. Smaller one is prey robot, whereas the larger one is interfering robots. Interfering robot size represents the signal jamming scope. Agent in the both sides learning a stochastic policy so that model of robots has good generalizability and transferability. The next, we experiment with ICL method. We design two curriculum lists. Both lists have training step is 2000, and the symmetric ICL is scenario 1, scenario 2, scenario 3, and scenario 4. And each scenario has replay buffer size is 1000. And another list asymmetric ICL is scenario 1, scenario IRAS, scenario 3, and scenario 4. IRAS is a scenario which the interfering robot added into scenario 1. The list of replay buffer is 500, 700, 900, and 1100. The curriculum list 1, symmetric ICL result from the table we can get from computing time. The symmetric ICL has less computation time, and from final reward, only the list scenario 1, 2, 3, 4 has higher reward, and from win rate, the list 1, 2, 3 and the list 1, 2, 3, 4 has better result. What can we get? Symmetric ICL could reduce running time and better promotional within more constraints, which is mean in a complex scenario, symmetric ICL has better result. In curriculum list 2, asymmetric ICL, from reward indication, we can obtain each list has better, or all the lists have, all the figure indicates better reward, and from win rate, asymmetric SCL has higher win rate, and what we get. Succeed policy benefits the next target learning in curriculum. Replay buffer size affects the weight of the trained models. In conclusion, the contribution of this paper, we build communication models of the robots with cooperative and competitive relationship in multi-domain. And second, we propose SCL to solve modifying the model based on the local variation chains with transfer learning. And second, to optimize the collaboration model trained by deep referencement learning and analyze the difference and advantage between SSCL and ASCL method. Finally, thank you very much for your attention.
Hi everyone, I'm Wu Wendi, one of the paper writer. This paper is about multi-UAV adaptive path planning in complex environment based on behavior tree. First, I would like to introduce the content of this paper, which include introduction, scenario description, behavior tree organized path planning method, virtual target-based tracking method, simulation results, and summary. As for the content, in this paper, we consider a scenario which multiple tracking UAVs pursue a target UAV in a complex environment. Consider the faster airspeed of the UAV. The path planning needs to be finished in a limited time. Moreover, the complex environment may involve diverse geographical areas, which raises the challenges for the path planning algorithms. For the first challenge, we will adopt the real-time algorithms to keep the efficiency of path planning. For the challenge of environment diversity, we involve the behavior tree model and propose a behavior tree organized path planning method aiming at achieving adaptive scheduling of different path planning algorithms in different geographical areas. Furthermore, in order to take the advantages of multiple tracking UAVs, we propose a virtual target-based tracking method which can make the tracking UAVs pursue the target UAV collaboratively. The effectiveness of the proposed behavior tree OPP method and the VTBT method are verified by analysis and numerical results for different system configurations, showing that a substantial target tracking efficiency improvement may be achieved in comparison with the benchmark. First, in introduction, we describe the main contributions of this paper as follows. Firstly, a multi-UAV target tracking scenario is considered, which involves a complex environment containing no obstacle area, known area, and unknown area. When the tracking UAVs catch up with the target UAV, or the target UAV leaves a specified area, the tracking task is finished. Secondly, in order to overcome the challenges of real-time and diversity brought by the above scenario, this paper proposes a behavior tree organized path planning method, which can achieve the adaptive scheduling of different path planning algorithms for different areas. Thirdly, in order to fully take the advantages of multiple tracking UAVs, this paper proposes a virtual target-based tracking method which can significantly increase the success rate of target tracking. Lastly, the effectiveness of the proposed method is verified through simulation experiments. From the experimental results, it shows that the behavior tree OPP method and the VTBT method can largely improve the target tracking efficiency. As for scenario description, in this scenario, multiple tracking UAVs catch up with a target UAV which views through multiple diverse areas. We divide the environment into three areas, which are known obstacle area, known area, and unknown area, respectively. In the known obstacle area, the path planning algorithm does not need to consider the influence of obstacles, and the tracking UAV can fly straight to the target UAV. In the known area, the positions of obstacles are known and can be considered into path planning. For the unknown area, the obstacles are not completely known or temporarily changes. The path planning algorithm needs to fully consider the effects of unknown obstacles. Based on this scenario, we considered a behavior tree organized path planning method. First, we describe the behavior tree's design. Starting from the root node, the behavior tree firstly takes the condition node that judge whether the target UAV has been successfully caught. If the target UAV fails to be caught or return failure, it will traverse to the child node to determine whether the target UAV is in the area under consideration. If it is not in the effective area, it returns failure. If the target UAV is in the effective area, its position will be obtained and transmitted to the tracking UAVs. When in the no-obstacle area, tracking UAVs can fly straight to the target UAV. Otherwise, the IARA star algorithm or D-starlight algorithm will be adopted adaptively. The behavior tree iterates through all nodes every 1 second until the end of the target tracking tasks. As for the action node design, the straight action node controls the tracking UAV to fly straight to the target UAV. The calculation cost of path planning is almost negligible, and the planned path is highly efficient. For the IARA star action node, it will allow the IARA star algorithm and provide a feasible path under any time limit. The longer the time, the better the path, so that the real-time performance of the algorithm can be guaranteed. In the unknown area, the environment is not completely known by the tracking UAVs, which may lead to the appearance of unexpected obstacles. At this time, the D-starlight action node is selected. The D-starlight algorithm is used to deal with the path planning in unknown environment. The core of the D-starlight algorithm is assuming that the unknown area is all free space. On this basis, the path planning is implemented in an incremental way, and the shortest distance to the target position is found in a limited time. In order to take the advantages of multiple UAVs, we proposed our dual target-based tracking method. This method is based on the idea of multiple hunters rounding up a pariah. One hunter is selected as the main hunter, and the remaining hunters plan their passes according to the possible positions of the pariah at the next moment. This part is the virtual target-based tracking method pseudo-code. Well, in order to verify the tracking performance of the behavior tree OPP method, we may select the D-starlight algorithm as the OPP method and the benchmark. For the behavior tree OPP methods straight, ARA star and the D-starlight algorithms are used to plan the passes for different areas respectively. A trajectory comparison between the BT-OPP and the OPP methods are shown in Figure 4a and Figure 4b, respectively. In this testing, the airspeed of the tracking UAV is the same as that of the tracking target UAV. From the result, we may see that the length of the planned pass by the behavior tree OPP method is apparently shorter than the OPP method. Furthermore, the tracking UAV with the behavior tree OPP method finally catches up with the target UAV successfully, but the OPP method may not. Well, in Figure 5, if the final distance is greater than 0, it means that the target UAV cannot be caught. From the figure, we may see that the final distance increases with the increase of the initial distance, but the tracking efficiency of the behavior tree OPP method is obviously higher than that of the OPP method. When A higher than 1.5, the final distance of the behavior tree OPP method was always 0, which means the target UAV can be always caught. In this paper, a multi-UAV target tracking algorithm called VTBT method is proposed, which aims at increasing the chance to catch up with the target UAV. We compare the flight trajectories under the behavior tree OPP methods with a single tracking UAV. We can see in Figure 6a and multiple tracking UAVs, Figure 6b. In the multi-UAV case, the virtual target distribution is calculated by the VTBT method in order to verify the optimization effect of the multiple tracking UAV case, the single tracking UAV case. And this experiment designs the path planning efficiency comparison of the two cases, as shown in Figure 7. The x-axis is the airspeed ratio of the tracking UAV to the target UAV. The y-axis is the time step index, and the z-axis is the time steps that the target UAV being caught. According to the results, it can be seen that under the same number of tracking UAVs, The tracking efficiency increases with the increase of A. Furthermore, with the same A, the more tracking UAVs there are, the faster the target will be caught. Finally, this summary is about this paper considered a multi-UAV target tracking scenario in a multi-geographical area, which involved the challenges of real-time path planning and environment diversity. We proposed to use behavior tree to solve the two challenges and introduce the behavior tree OPP method, which could automatically select the appropriate path planning algorithms according to the environment conditions. Moreover, in order to increase the tracking performance, we propose the VTBT method that fully utilizes the advantages of multiple tracking UAVs. The simulation results showed that the behavior tree OPP method could largely improve the target tracking performance more than the classical OPP method. When involved with the VTBT method, the behavior tree OPP could further decrease the tracking time. That's all. Thank you.
Hello everyone. I am glad to have the opportunity of making this presentation here. My topic today is adaptive online estimation of thrashing-avoiding memory reservations for long-lived containers. My presentation consists of 4 parts. I am going to introduce the background and motivation first. Then I will introduce our work, MIR+ and DeepMIR, and finally give our experimental evaluation results and make a conclusion. Now, let's start with background and motivation. With the recent technical breakthroughs in big data, a dramatically increasing number of heterogeneous in-memory computation workloads, including machine learning, streaming processing, interactive query, and graph computation are being deployed on shared clusters in data centers. These kinds of workloads dealing with huge amounts of data are called long-running applications, which have become the dominant workloads. Clusters rely on resource managers, such as Yang, to allocate resources for applications. These managers schedule computing resources by packaging them as containers. Different from traditional short-lived containers built to deal with batch jobs, containers for long-running applications stay alive until an application completes, so it is named long-lived containers. Our work concerns on how much memory should be allocated for these kinds of containers. From previous work, we learned the concept of memory reservation elasticity, that slight reduction of memory supply under over-provision has no serious impact on performance. This property benefits from memory managers' two protection mechanisms. When the memory is insufficient, garbage collection will be triggered to free memory, or the program will be spilled to the disk. Under this situation, the slight performance penalty caused by insufficient memory supply is acceptable. This means once we find the performance inflection point, we can find the best balance between memory utilization and application performance, and this inflection point can be considered as optimal memory reservation. A leading technique to estimate optimal memory reservation is MIR. MIR executes a pilot run, and then uses histogram analysis to learn the rule of memory occupation and estimates an optimal memory reservation through iterative search. Our work is based on 2 observations on this work. The first observation is that MIR has the characteristic of self-decay. The estimated result decreases progressively and irrevocably before termination, which limits the opportunity for correction. To achieve higher estimation accuracy, we refine step size of iterative search to rectify the estimation result. There are 2 cases of the estimated memory that meets the termination conditions: excess reservation and insufficient reservation. In our work, a step size is introduced to approach in different directions. In the case of insufficient reservation, the memory is gradually increased. In the case of excess reservation, the memory is gradually reduced. It is not difficult to prove that as long as the step size satisfies the following 2 formulas, more accurate estimation results can be obtained. We name the estimation strategy with the approach step added as MIR+. The green path in the figure is the incremental approximation process. After the termination of iterative search, MIR+ will approach in different directions according to different termination conditions. Another observation of our work is that MIR requires applications to experience inefficient execution caused by the termination conditions, which may not be accepted by users. Based on this observation, we make full use of the abundant historical data generated in MIR+ to eliminate the effect of termination conditions on application performance and propose an estimation model based on reinforcement learning. The model consists of two units, actor and critic. The actor is responsible for providing policies to map the system states to the probability of memory reservation. The critic acts as a value function. It passes judgment on the chosen action about how much it benefits the environment and provides useful reinforcement feedback for adjusting the policy. Actor and critic are both implemented by neural network. Actor consists of three layers: input layer, hidden layer, and output layer. The inputs of input layer are states coming from environment. The value of each neuron is the weighted sum of neurons in the previous layer, except that the values of input neurons are provided by the environment. The mapping of neurons between each two layers is linear, which limits the expression ability of the model. Therefore, we introduce nonlinear factors by activation function to make the neural network approach any nonlinear function at will. The neurons in output layer correspond to the action that how much memory reservation is set for this application. They finally go through a softmax function, with the help of which the outputs are transformed to values between 0 and 1, and the sum of them is equal to 1. In other words, each output stands for the probability that the action should be chosen. The greater the probability, the more likely it is that the action will bring the greatest benefit. The basic structure and parameter form of critic are similar to that of actor. The only difference is that the output layer has only one neuron, which is the score given by the critic. Once it figures out the value is combined with reward from environment to finally compute the loss, which will be used to guide the actor and critic to update. Both actor and critic interact with the environment, which is the cluster running the application. On the one hand, it runs the submitted application under memory reservation determined by the actor. On the other hand, it returns the state changed after executing the action as well as the reward that measures how much it benefits from the action. We also define some interaction information parameters to make the model run. States that are provided by the environment include increased execution time compared to initial run, expectation of memory footprints, the most frequent values of memory footprints in histogram analysis, and corresponding frequency of the most frequent values. The target of our model is to save memory and remain good performance at the same time. Therefore, the more memory is saved and the less time it takes to complete the application, we are closer to our expectations. Here we define reward as a function like this. In terms of action, each neuron of actor's output layer corresponds to a specific memory reservation setting. We name this reinforcement learning-based estimations JTG as DeepMIR. The estimation model is replaced by a reinforcement learning-based actor-critic learning model. Every time a submission comes, Resource Manager allocates memory resource with the model's guidance. It is able to stop before the estimation result exceeds the performance inflection point, so that users will never experience bad application performance. Since MIR Plus and DeepMIR have different superiority and conditions for execution, they are suitable for different cluster stages and complementary to each other. A cluster begins with initial stage. There is no prior experience when the cluster is just starting to work, so MIR Plus is adopted, sacrificing application performance several times to conduct the estimation. In the meantime, model training begins. A large amount of historical application execution data is produced in this stage, which is source material for model training. Once the cumulative rewards reach a threshold, we turn to adopting DeepMIR and the cluster transforms into a stable stage when applications always perform well. Next, I will introduce the experiment part. We conduct all the tests on a cluster of virtual machines equipped with 1-core CPU, 12 GB memory, and 200 GB virtual hard disk. We use Ubuntu with Hadoop Yarn and Spark deployed. Both histogram analysis model and actor-critic learning model are implemented with Python. We run 4 representative workloads coming from Spark Bench, Spark's benchmark performance test project for evaluation, in order to simulate the characteristics of application execution in industry. We configure the input size of each workload. We take MIR as a baseline and evaluate our work. Our results confirm that MIR Plus has the best estimation ability, showing the best accuracy in 3/4 of the tested workloads and the least average relative error of only 0.105. DeepMIR comes after with average relative error of 0.688. They both perform better than MIR, whose average relative error is 0.875. In the experiment, we run PageRank and triangle count in initial stage to train the model and use the model to estimate on shortest path and SVD++ in stable stage. So we can also make a conclusion that DeepMIR has the advantages of excellent generalization ability. As for memory utilization, the memory utilization of MIR Plus and DeepMIR is always greater than MIR, and their average utilization is about 21%, twice that of MIR. The peak memory utilization of MIR Plus and DeepMIR is 47% and 49% respectively, while the peak of MIR is only 23%. As for application performance, both MIR and MIR Plus experience a cliff of performance degradation in the process of estimation. This is caused by termination conditions, to meet which the application may go through a low performance run. MIR Plus may experience more times of low performance for the stage of approximation may approach the optimal under inadequate reserved memory. In terms of DeepMIR, its model always gets low reverse while setting reserved memory size less than the performance inflection point in the process of training. Drawing a lesson from history, it mostly chooses memory settings that larger than inflection point to gain high rewards. This can explain why using deep mirror, workloads can always maintain satisfying performance. In a conclusion, our work aims to estimate optimal memory reservation to balance performance and resource utilization. Based on 2 observations on mirror, we propose 2 improved estimation schemes by adding a new step of approximation and building an unsupervised reinforcement learning model without termination conditions, which show good results on estimation accuracy, generalization ability, resource utilization, and application performance. That's all for my talk. Thanks for watching and listening.
Good afternoon, everyone. My name is Ma Yuying. I'm from Chongqing University in China. I am very pleased to join this conference. The topic of my presentation is a novel probabilistic performance-aware approach to multi-workflow scheduling in the edge computing environment. My presentation will include 3 parts: background information, the main work we have done, and conclusions we have got. In recent years, with the rapid development of Internet technology, users can experience various applications on mobile terminal, such as AR and VR. However, these powerful applications have strict requirements on the computing power, processing power, storage, and battery of mobile devices. In order to solve the problem, some people proposed to offload computing tasks from mobile devices to the cloud and make use of the scalability of cloud resources. However, the traditional cloud is far away from users, which will cause delays, network congestion, and other problems. It's considered to offload computing tasks to the edge cloud for execution. Then, what is edge computing? Edge computing refers to enabling technologies allowing computation to be performed at the edge of the network. Here, we define edge as any computing and network resources along the path between data sources and cloud data centers. For example, a smartphone is an edge between body things and cloud. A gateway in a smart home is an edge between home things and cloud. A micro data center is the edge between mobile devices and cloud. Why I choose this item? I think it can be illustrated from the following 3 parts. First, most of the existing methods of scheduling workflow in cloud computing. In the edge computing, research is not sufficient. Existing heuristic bio-inspired algorithms with static and time-invariant performance models can be ineffective in dealing with real-world, edge environment-oriented workflow scheduling requirements, where performance of edge servers and platform-level infrastructures themselves are with highly unstable and time-vary performance. Second, comparing with traditional cloud computing. Edge computing environment has low latency, security, avoid network congestion, and can handle delay-sensitive tasks. Third, workflow scheduling in edge computing environment is also a hot topic in academia and industry. The meaning and aim of this research contain 2 parts. Firstly, reducing the cost of edge computing system, where the connection between the user and the server can be successfully established. Secondly, reducing workflow completion time. Users have better experience. Now let's move to the system model and problem formulation of our research. The system model is shown in Figure 1, and edge computing environment can be seen as a collection of multiple edge servers usually deployed near base stations. By this way, users can allow to offload compute-intensive and latency-sensitive applications. For example, AR, VR, and AI to edge servers. Within an edge computing environment, there are M users, denoted by acetyl-U, and NAT server stations, denoted by acetyl-ES. Each user has an application in terms of a batch of tasks organized by a workflow. To be executed, a user's mobile device is allowed to offload tasks to nearby edge servers. In this work, we consider time-varying performance of them. To be specific, we consider that the historical execution time of a certain workflow task upon an edge server, i.e., a discrete random variable x with DOM x, can be described by an empirical probabilistic distribution. Formula 1 is a cumulative distribution function of execution time and cost, where C is deadline value. The probability that the resulting workflow completion time and cost meet a deadline constraint can be estimated according to the following performance aggregation functions at probabilistic performance aggregation rules in Tables 1 and Tables 2. Based on the above analysis, the problem of probabilistic performance-aware multi-workflow scheduling can be described as follows. Given multiple works Wi, we are interested to identify an edge server assignment plane of Wi with the highest probability that the workflow completion time and cost met the deadline constraint. Describe the resulting with the following formulation. Formula 2 is the highest probability that the workflow completion time and cost meet the deadline constraint. There are two constraint conditions. The first is the proximity constraint. The distance between the server and the user is less than the coverage of the server. The second is at the same time. The task can only be executed on an edge server, and Xij is a Boolean value. Based on the problem, we present novel schemes of coding rules, decoding rules, and updating rules of Firefly algorithm that deal with the location-aware and proximity-constrained multi-workflow scheduling problem. DFA generates an initial population, set the number of iterations, by comparing the target function to make each individual move to the optimal individual, and finally get the optimal scheduling. The algorithm consists of 3 steps, including Firefly evaluation and Firefly update. In DFA, a schedule is an individual, described as a vector of integer values. The length of a vector is the same as the number of tasks in a workflow. Ith element of the individual indicates to which server the ith task of the workflow is scheduled to execute. Figure 2 gives a sample of individual coding at a given workflow deployment, assuming that the workflow consists of 8 tasks, and is within the coverage range of by server 2, 3, 4. In this schedule, tasks 1, 4, 6 are scheduled to be executed on server 3. Tasks 2, 3, 7 are scheduled to on Server 2 and Task 5-8 are scheduled to Server 4 respectively. The stipulation of update is that the darker 5 line moves towards the brighter one. The population is updated iteratively, and the scheduling strategy keeps being optimized. An example showing the update process is given in Table 2. The movement process is as follows. So with DFA, we can obtain the optimal scheduling of workflow. Now, I'd like to move on to experiment and result analysis. We use the 3 well-known scientific workflow templates, namely CyberShake, LIGO, and SIPLT as shown in Figure 3. We evaluate the performance of our proposed method by comparing it with 3 existing methods, namely PureFA, GA, Greedy, and Random. We consider that all AG servers are with 3 different types of results configurations and charging place. TP1, 2, 3 are shown in Table 4. The positions for AG servers and users are based on the dataset illustrated in Figure 4. We tested the completion time of a task on 3 types of AG servers and different periods, i.e. A, B, and C, as shown in Figure 5. As can be seen, the period of 5A shows the weakest performance fluctuations, while 5C shows the greatest. And the periods of 5ABC we show in Figures 6 to 8. The comparison of scheduling performance of different methods in terms of deadline constraint, satisfaction rate, workflow completion time, and cost. As can be observed, our method-based random, PureFA, Greedy, and FAGA in terms of average deadline validation rate. Moreover, our method clearly achieves lower workflow completion time and cost. The advantage our proposed method is achieved because the fact that traditional workflow scheduling algorithms are designed on the cloud without taking into account the real-time performance fluctuations of AG servers. However, this is not real in the edge computing environment, where each server fluctuates in performance. From the above data, it can be seen that our method has a great advantage when server performance fluctuates sharply. This is because our method takes performance into consideration to schedule workflow, makes it superior to its peers in terms of completion time and cost. The above is our research summed up. Firstly, our aim is to obtain the better scheduling strategy with the highest probability that the workflow completion time and cost met the deadline constraint. Secondly, based on the existing method, we add the proximity constraint and consider the real-time performance fluctuations of AG servers. Thirdly, we proposed a discrete 5-line algorithm to solve the problem and get the optimal scheduling strategy. Finally, the stimulation experiment results show that our proposed method is clearly outperform traditional ones in terms of cost and completion time. Okay, Right then, thank you for your time and attention.
Hello everyone, I'm a student from Chongqing University. Due to the impact of COVID-19 in this year, we meet online. It's still my honor to introduce my paper RCFC, a region-based POI recommendation model with collaborative filtering and user context to all of you. I hope we'll have a good time online. I will make this presentation from the following aspects, which is in line with the structure of my paper. Location-based social networks such as Facebook, Twitter, and Foursquare facilitate people's outdoor activities by recommending nearby locations in real time. So, we call these locations points of interest. POI recommendation encourages users to share their experiences by check-ins, which gives us the chance to explore user preferences by this check-in data. Collaborative filtering, no matter based on user or item, is extensively investigated in recommendation system and widely used in industry. However, it faces a huge challenge since users just check in a few locations and that causes the data sparseness. And secondly, the key of reasonable explanation is to make full use of user context, as it greatly influences the user's decision on visiting a location. Therefore, these two challenges inspire us to improve our own POI recommendation system. In our previous work, we proposed a deep recommendation framework by combining restricted Boltzmann machine with non-negative matrix factorization. Furthermore, we construct a recurrent neural network based on self-attention to predict the next locations of users. We also tried some explorations by modeling geographical and social influence. In our RCFC model, different from our previous work, we focus on the region factor that could improve CF in POI recommendation. Moreover, we still consider the user context, such as geographic distance and local and location category. This is the whole framework of RCFC. It consists of three parts. Firstly, we cluster locations into different regions for capturing users' preference on regions, and then incorporate that into CF. Secondly, after obtaining regions, we search the activity area for users in order to find limited candidate locations, and next use a non-linear model to calculate the probability of geographic distance. Thirdly, we capture the category level transition pattern between locations by a novel category pairing method. Now, I'll show each part in detail. We have a set U of users, a set L of locations, and a set C of categories. Each location is denoted by its longitude, latitude, and the category. The original user vector indicates the locations he has visited. For widely distributed locations, clustering them into regions by k-means is benefit for alleviating the data sparseness, since there is a huge number of locations. After clustering, suppose there are Q regions R. Based on region, we use a new user vector where it denotes the number of times user has visited on different regions. Then, we calculate region similarity between one user and others, and get a score of the user, which indicates the probability he will visit this region. Therefore, according to the region that target location belongs to. We use region score to enhance the normal collaborative by combining them. This is our region-based collaborative filtering, which is called RCF. The goal of RCF is to alleviate the negative impact caused by data sparseness. The major user context for POI recommendation is geographical distance. Users tend to visit locations that are closer to their current location. And we adopt a power law distribution to model the probability. In order to obtain this model, we transform it into logarithmic form. Then, the locations in a region that users have visited can be divided into many small circles, which we call activity area. So, we only calculate geographic score for locations belong to users' activity area. This is because we want to filter out those far away. Let's go on. Categories usually have semantic information, reflecting functions of locations, and we present a novel pairwise method to model the influence of category. If a user has visited two categories, then we can say there is a transition relationship between them. Next, we get a co-occurrence matrix of category. If user has visited the category before, we calculate its probability according to users' check-ins in this region. Otherwise, we use the co-occurrence matrix. Now, we are able to combine all the parts. We first compute the category score and then get the final score of RCFC. Finally, we sort the scores of all candidate locations and recommend top key locations to users. I just showed the important contents of our model. If you're interested in it, please read our paper. We employed two real-world datasets that are collected from two cities on Foursquare. One is Los Angeles, the other is London. Both two datasets are much sparse. We randomly select 70% of the locations of each user as training data and the remaining 30% as test data. We firstly choose the optimal parameters of our RCFC and then evaluate that with other recommendation models. As many recommendation systems, we adopt precision, recall, and F1 score to evaluate the performance. To comprehensively demonstrate the effectiveness of our model, we compare them with 5 popular models. RCF is the region-based collaborative filtering that doesn't incorporate the context. There are 3 parameters of our model. Alpha, which the region-based CF, and impact of context. From the figure, it's observed that all curves first go up and then go down in both datasets. This indicates that with the increase of alpha, the performance of a model can be improved by region-based CF. But then, excessively ignoring the user context will cause the performance to decrease. For the outlet dataset, the optimal alpha equals 0.7, while alpha equals to 0.6 is most suitable for the long dataset. Beta with the geographic distance and category. On one hand, the curves of outlet dataset have clear upward trends before beta equals to 0.5, but then become flat gradually, which reveals that geographic distance has a limited improvement. On the other hand, what top key equals to 10 and 15, the curves of long dataset go down significantly after reaching their peaks, which shows that too much consideration of geographic distance will bring negative effects. For the outlet dataset, the optimal beta equals to 0.9, while beta equals to 0.5 is most suitable for the long dataset. Q determines how to cluster locations into regions. There are many significant differences between two datasets. A huge decline happens for the outlet dataset when Q equals to 2, which indicates that few regions may result in insufficient clusters, especially at the beginning. With the increase of Q, the advantage of region comes into play gradually. In contrast, for long datasets, Q equals to 2 doesn't destroy the performance. That may be due to characteristics of the dataset, because each city has different distributions of locations. Overall, there are many obvious fluctuations on both datasets. For the outlet dataset, the optimal Q equals to 11, while Q equals to 16 is most suitable for the long dataset. The performance comparison is shown in this figure. Firstly, from a whole perspective, RCFC is obviously superior to other recommendation models in terms of both precision and recall. Although DMF is a state-of-art deep model for recommendation system, it's only better than NMF and POP. One possible explanation can be that DMF depends on the structure of neural network to a great extent, and it's also very sensitive to different datasets. Secondly, the classic CF model performs well on both datasets, which fully proves why it can become the widely used recommendation model in industry. And BRP still has an excellent performance at present. RCF only considers the region factor and ignores the impact of user context. Hence, it doesn't outperform RCFC. Meanwhile, RCFC can make reasonable explanation for recommendation according to region and context. Well, in our RCFC model, we put forward two challenges in POI recommendation. One is the data sparseness caused by users who just visit few locations, and the other is that it's hard to make reasonable explanation for recommendation from the perspective of real world. Therefore, for the sake of alleviating data sparseness, we firstly present a region-based CF by clustering locations into different regions. Secondly, we explored influence of two user contexts like geographic distance and location category to enhance the explanation of recommendation. We construct experiments on 2 real-world datasets connected from 2 cities on Foursquare, and the results demonstrate RCFC is superior to some popular POI recommendation models. For future work, we will compare different clustering methods to make the regions more accurate. These are references we have, and thank them so much for giving us great inspiration. At the very end, thanks for all your listening.
Distinguished colleagues, ladies and gentlemen, I appreciate the opportunity to share my ideas with all of you. My topic is focused on cooperative offloading in mobile edge computing-based Internet of Things. I'm going to give this talk in 8 parts. First, what is mobile edge computing? As we know, MEC was proposed by ETSI, the European Standards Organization. MEC offers IT service and cloud computing capabilities at the edge of the mobile network in an environment that is characterized by proximity, ultra-low latency, and high bandwidth. Compared with cloud computing, the cloud center is far away from user devices, but the MEC server is at the edge of the network, which is close to the devices. All data should be transmitted to the cloud center, but the devices only transmit data to the MEC server at its access point. Although the cloud center has extremely large capacity to process data, but tremendous user data will induce long delay, traffic block, and low QoS, etc., especially in 4G networks with countless IoT devices. Compared with fog computing, data are processed within fog nodes in fog computing. But as for edge computing, data are processed on the pre-located device that is physically close to the sensors. Why we use offloading? Offloading is beneficial when large amounts of computation are needed with relatively small amounts of communication. Let's look at the equation. P is the power for local computing, data process, and communication separately. The same task thus takes C divided by S seconds on the server and C divided by M seconds on the mobile system. It takes D divided by B seconds to transmit and receive data. When the equation is greater than 0, offloading is beneficial. Our motivation for cooperative offloading. For traditional offloading schemes, long-distance communication consumes more energy at the same transmitting rate. Usually, an IMD has some labels distributed around it randomly. The average transmitted rate to the AP with distance follows the negative exponential distribution, which means that the less distance between IMDs, the much less energy will be consumed. Then, cooperative offloading will save energy for less distance at the same power. Our proposal is to select one neighbor among all neighbors of the target IoT mobile devices for energy-efficient cooperative offloading with delay constraint, since some tasks can only be divided into limited parts for execution. The goal is to optimize the energy efficiency with delay constraint. If the execution of a task has no delay constraint, it can be executed with low CPU frequency and thus the low energy consumption. But many applications are data sensitive, which should be executed at much higher frequency, so we should use offloading to save energy. This is the scenario of our proposed system model. We consider a network consisting of one target IMD, a set of mobile users neighboring to the IMD as candidate cooperative nodes to help uploading, and one access point integrated with an MEC server providing rich computation resources. The IMD has computing tasks which can be processed locally, offloaded to one of its neighbor nodes or to the MEC server to execute. The IMD offloads tasks to its neighbor node and to the MEC server through different links. We have four assumptions. First, the D2D link and the cellular link do not interfere with each other by deploying over different frequencies. Second, the channel state remains unchanged during the offloading period of one computational task. Third, computation task can be divided into 4 different parts for execution. Last, costs for result downloading are not taken into account because the results are usually short. We have a set of neighbors of the target IMD. The task length is divided into 4 parts, which has the delay constraint of T. The whole task is summarized into 3 processing stages, which are local processing, neighbor processing, and server processing. Each stage has its own processes. Equation 2 is the computation time used for a task. Then the delay constraint for local computing at the target IMD is derived as equation 3. The energy consumption for local computing at the target IMD is derived as equation 5. We get the equations of the transmission rate, the offloading delay, and the energy consumption separately for offloading to a neighbor node at the target IMD. We get the equations of the transmission rate, the offloading delay, and the energy consumption for offloading to the MEC server separately at the target IMD. For neighbor node processing, we get the delay constraint for computing at the neighbor node by equation 14. We also get the energy consumption for local computing at a neighbor node by equation 16. As for computation offloading at the neighbor, we get the equations of offloading delay and the energy consumption for task offloading from the neighbor to the MEC server. For the stage of MEC server processing, we get the equations of the execution time and the delay constraint. The delay constraint can be derived as equation 25. For problem solution, we got the total consumption by equation 27 calculated by a neighbor node. The delay constraint and the minimization problem is formulated as P1, which is a convex problem. By solving P1 for each neighbor node, the neighbor with the least energy consumption will be got. Since the time complexity to solve problem P1 is high, we also get a new neighbor selection scheme with less time complexity, which is related to the combination rates. For the metric of the maximum task length, which discloses how many bits of a task are supported within the given delay constraint, is described by P2. Problem P2 is a linear problem and can thus be efficiently solved via standard concave optimization techniques. For the numerical results, we evaluate the performance of the proposed cooperative offloading design compared with two benchmark schemes. One is local computing only, the other is offloading without neighbor aided. For our proposed schemes, one is offloading with the neighbor of weighted value. The offloading neighbor is selected with respect to equation 29. The other is offloading with the best neighbor, which is selected by solving problem P1. We set 20 neighboring nodes of the target IMD randomly at different intersections in the given rectangular area, which is evenly divided into a 26 multiplied by 11 grid. For the result of the average maximum length of tasks, the length increases as the time of delay constraint increasing. Our proposed scheme, that is offloading with the best neighbor, outperforms other schemes in the term of supported maximum length of tasks at any time constraint. From this figure, we got that the minimum energy consumption decreases as the delay constraint increasing. Our proposed scheme has the minimum energy consumption at any constraint of time, and we get that partial computation in different nodes by offloading can reduce energy consumption in total, because computation energy consumption will increase exponentially with the task length within limited time constraint. For this figure, we get that the longer of tasks, the higher for energy consumption. The minimum energy consumption increases exponentially as the length of task increasing. But our proposed scheme has least energy consumption at any settings of the task length. We conclude the presentation in three aspects. First, offloading can help in saving energy consumption, especially with strict time constraint. Second, cooperative offloading is more energy efficient than direct offloading. Last, offloading with the neighbor of weighted value is acceptable for low computation complexity. That's all for my presentation. Have a good day and thank you for your attention.
Hello everyone. Today I would like to present my paper T2I CycleGAN, a CycleGAN for maritime road network extraction from crowdsourcing spatial-temporal AIS trajectory data. I'm Xuankai Yang. I'm from North China University of Technology. My presentation will cover the following aspects: background, method and models, experiments, evaluation and conclusion. With the increasing international trade, accurate and up-to-date maritime road network data becomes vital. It can be used in many applications such as threat detection and traffic control. In recent years, with the rapid developing of mobile sensors and cloud computing, a large amount of crowdsourcing vessel trajectory data or automatic identification system data has been generated and collected. Such historical crowdsourcing trajectory data provides a new opportunity to extract the underlying maritime road network. The vessel trajectory data, or AIS data, are usually large in scale and collected with different sampling rates. Extraction of maritime road network is very challenging. Traditional road network generation and maintenance methods, such as field surveys, are not feasible. This is because the maritime road network is not man-made structure and cannot be obtained by observation. As for the approach proposed for extraction, in order to ensure the accuracy of the extraction results, road network extraction needs to use real map data, such as OpenStreetMap data, as a training set or as a reference standard to distinguish the data in the road region from outside the road region. However, maritime road networks are composed of customary routes for ship navigation rather than man-made roads, and the structure of the global maritime road networks itself has not been fully documented. This makes it unrealistic to find enough real or reliable maritime road network data as experimental training sets for maritime road network extraction. So, to overcome the challenge mentioned above, in this paper, we propose an unsupervised CycleGAN-based method named T2I CycleGAN, which means trajectory to image CycleGAN to generate maritime road network from trajectories. The extraction procedure is presented in the figure, which is composed of two steps. The first step is trajectory data transition, which pre-processes the raw trajectory data and extracts features from them. The second step is maritime road network extraction, which trains the generator and discriminator of T2I CycleGAN with the extracted features and uses the model to extract the maritime road network. First, the trajectory data is pre-processed, then the data features are extracted from trajectory transition, and the results are divided proportionally to obtain the trajectory data sample set. At the same time, the road network style data is proportionally divided to obtain the maritime road network sample data. And finally, the divided two parts of samples are put into the trained T2I CycleGAN model to get the generated maritime road network. The key contributions of this paper can be summarized as follows. We propose an unsupervised learning-based maritime road network extraction model T2I CycleGAN. The method that doesn't rely on paired trajectory and road network samples for model training. Paired training data consists of training examples where the correspondence between them exists. For example, as shown in Figure 1, xi presents the trajectory points of the road network, and yi represents the corresponding road network segments. Second, we use a trajectory data transition method to propose trajectories with different sampling rates and at dense layers in CycleGAN to make it able to handle situations without recognized benchmark data as a reference standard. And the third, experimental results show that the proposed method can automatically effectively extract maritime road network from crowdsourcing spatial-temporal AIS trajectory data without real or recorded maritime road network data as an experimental benchmark by comparing with the related work. As shown in the figure, generative adversarial networks we use in T2I CycleGAN is a two-way cycle network structure composed of two mirrored CGAN structures. The two CGANs share two generators, generator A to B and generator B to A, and have two associated adversarial discriminators, discriminator A and discriminator B. In the forward process of the model training, generator A to B realizes the conversion from input A to generated B, and generator B to A realizes the reverse conversion from generated B to cyclic A. The result generated B is compared with the real images by discriminator B, which can facilitate the generator to generate results that are indistinguishable from real images of maritime road network. In order to further standardize the image conversion function, two cycle consistency losses are used in the model. As you can see in the figure, for each image X from domain X, the image translation cycle should be able to bring X back to the original image. Similarly, for each image Y from domain Y, G and F should also satisfy the cycle consistency. The cycle consistency losses are obtained by comparing the results with the real images. The data we used in the experiment is the AIS data of all cargo ships in February 2016. Our target area is Bohai Sea. AIS data includes vessel's name, call sign, MMSI, IMO, ship type, destination, ship width, and other static information such as UTC, latitude, longitude, direction, speed, and status. The experiment uses 4 columns of MMSI, UTC, longitude, and latitude from the dataset. A dataset sample is shown in Table 1. The total amount of AIS data of Bohai Sea cargo ships is 1.5 GB. The data contains over 109,645 travel records of ships. The experiment runs in a Linux environment. Model implementation and result analysis based on Python and PyTorch. The model is trained with a single NVIDIA Tesla K40C GPU, and the video memory is 12 GB. The figures show the extraction results of Maritime road network in the Bohai Sea area. In order to compare and evaluate the extraction results of T2I CycleGAN, this paper compares and evaluates CycleGAN, simplified DeepMG, and the NIBLAC-based extraction method. It can be seen from the figures that although the shape of the extracted road network is basically the same as the result obtained by the T2I CycleGAN model, there are more noisy road segments in the results of CycleGAN. The result obtained by the T2I CycleGAN model is well optimized in noise processing. The DeepMG framework uses a CNN-based supervised training method for road network extraction. Due to the small amount of ship trajectory data used in our experiment, overfitting occurs when these data are used for T2RNet training. In addition, we have not implemented the topology construction part of the DeepMG framework, which will be implemented in the future work. The result shows that, in the case of using the same test data, the results obtained by simplified DeepMG have poor integrity, but the details are richer. As for the NIBLAC-based method, the main idea of the method is to use a local sliding window filtering algorithm to filter those grids that are not on the marine lane. The processing result of this method generates many shortcuts that do not exist on the real map, and the T2I CycleGAN model has higher connectivity in processing the data. And because of the lack of maritime road network benchmark data, we took the trajectory point data in the Bohai Sea area as a reference sample, and manually extracted the maritime road network in this area as a reference. Table 2 representatively calculates the precision recall and F1 score of the comparison method. Table 2 shows that the results extracted using T2I CycleGAN have better performance on each indicator. Using CycleGAN can improve the recall rate of the maritime road network, but the accuracy of the results obtained by simply using CycleGAN is low. It shows that the dense layer added in T2I CycleGAN can effectively reduce the error road in the extraction result. The extraction results of simplified DeepMG and the NIBLAC-based extraction method are relatively low. This work is supported by National Natural Science Foundation of China, and we thank the Ocean Information Technology Company, Electronics Technology Group Corporation for providing the underlying dataset for this research. And thank you.
Hello, everyone. My name is Mengmeng Zhang, a student of North China University of Technology. The title of this paper is Where is the Next Path? A deep learning approach to path prediction without prior root networks. This paper is composed of 6 parts, which are introduction, problem description, geometry translation, trajectory prediction, experiment and analysis, and conclusion. First, let's introduce the first part. The first part mainly introduces the research background and the contribution of this part. In recent years, trajectory prediction is one of the most interesting and significant topics. Trajectory prediction plays an important role in many urban and metro transportation applications, such as path planning, logistics, and traffic management. As yet, there is little research work on trajectory prediction under road network constraints, and this existing work assumes prior road network information is given in advance. However, in some application scenarios, it's very difficult to get road network information. For example, the maritime traffic scenario on the wide open ocean. To this end, we propose an approach to trajectory prediction that can make good use of road network constraints without depending on prior road network information. The contributions of this paper are: first, we propose a deep learning approach to trajectory prediction based on LSTM model from large-scale crowdsourcing trajectory data. The method can predict the next road segment that moving objects would reach or pass without any prior knowledge about the road network. We label each trajectory with road segments and transform the trajectories into sequence of road segments. We also analyze the features of shapes that affect the trajectory prediction and select type of shapes and shapes direction of travel as features and joined with sequence of road segments as input of LSTM model. Third, we compare with the trajectory prediction method based on frequent sequence meaning algorithm. Experiments show that our method is more effective. This is the second part, which describes the definitions used in this paper and the description of the problem. Definition 1. Trajectory. A trajectory of a moving object, a ship or vehicle, is a set of trajectory points. Definition 2. Road boundary. A road boundary is a plane polygon set. Definition 3. Road segment. A road network is composed of multiple road segments. The problem described in this paper is: given a set of trajectories, for any trajectory of a moving object, infer the next road segment this moving object will reach. Geometry translation is the third part. In this chapter, it's mainly divided into following two parts: trajectory serialization under network constraints and motion feature extraction. The aim of trajectory serialization under network constraints is annotating each trajectory with a sequence of road segments. We firstly extract road boundaries with road segments annotation from large-scale crowdsourcing trajectory data. In order to extract the road boundaries, in our previous work, a parallel grid merging and flattening algorithm was proposed. But the extract road boundary polygons have a lot of jagged edges. We need to smooth the boundaries before future processing. For the details of the smoothing method, please refer to our previous work. An example result after smoothing is shown as the figure. The detailed network constrained trajectory serialization method could be divided into the following two steps: extract polygons of road segments and trajectory annotation with road segments. For the extract polygons of road segments, we apply the dt on the vertices of the smoothed road boundary polygons as shown in the figure. Then, the triangles outside the road and inside the cavity are flattened. Among the left triangles, Those with 3 common edges are at the road intersection. The centers of gravity of these triangles are the nodes of road network, and those triangles between 2 nodes are triangles on the road segments. The adjunct triangles are all traversed, and all triangles on the road segments could be determined. Then we can delete the inner edges of triangles on the road segments, and only keep the edges forming the road segments. In another word, now we have polygons of road segments. We can delete the inner edges of triangles on the road segments and only keep the edges forming the road segments. In another word, now we have a polygons of road segments. For example, there are a total of 5 road segments, and each road segment is composed of several triangles. Delete the inner edges of the road segment to get a road segment polygon. Given a trajectory, for each point of this trajectory, we start the road segment polygon which the point locates inside respectively. Thus, a trajectory is notated with road segments. Then we merge the repeated segments and get the final serialization results. There are 5 road segments in the road network. The black dots respect the trajectory points. We firstly annotate it with road segments, then get the final serialization results after merging. For the motion feature extraction, data and features determine the upper limit of machine learning, and models and algorithms are only approaching that limit. In addition to the trajectory serialization, we extract some motion features from the trajectory to improve the accuracy of the prediction model. In this paper, the features of shape type, direction, and road segment are studied. After statistics, we found that there is a certain relationship between the segments of the ship that the ship will sail to and the direction and shape type. As shown in the table, the distribution of direction always concentrates in a particular range. Trajectory prediction is the fourth part. The single-layer LSTM architecture in this paper is shown below. First, the input layer receives the tensors of fixed dimensions and lengths. Then, the LSTM layer consists of 256 layers, and then one consists of 128 layers. The fully contacted layers use the softmax as the activation function, and finally, the output layer contains layers with the same length as the output. According to the characteristics of the input layer of the natural network, the input vectors need to be divided into vectors of the same length. In this paper, the road segment sequence and features, direction, and shape type are selected as 3-dimensional input vector units. We introduce the step size, let step equals k, and then get a normalized k.3 2-dimensional input tensor. Experiment and analysis is the fifth part. The dataset used in the experiment is the real EAI data from January 2017 to February 2017. In the Bohai Sea area, there are totally 15,725 ships in the dataset. After the sampling, denoising, interpolation, and segmentation, a total of 10,688 trips record of 3,574 ships were extracted. The dataset used in the experiment is in the Bohai Sea area. For the experimental data, we used the controlled variable method to experiment. The experimental results show that the effect is best when step equals 5. The upcast respects the value of step, and the ordinate respects the value of micro precision, micro recall, and micro F1. We performed the model turning experiment firstly. The last 3 columns in the table respect micro precision, micro recall, and micro F1. We select this last fraction. From this table, we can see that the results show that the 14th group of experiments is the best. In the experiment, we compare our method with the trajectory prediction method based on frequent sequence pattern meaning algorithm. The average accuracy rate of the prediction is 0.812. The average recall rate is 0.824, and the average F1 value is 0.815. Compared with our work, the prediction results based on LSTM model are better than those based on frequent sequence. We believe that this is because the input of LSTM model include more features, including road segment sequence, direction, and shape type, while the PF method can only adopt road segment sequence as inputs. This part is the last part. In this paper, we study the problem of long-term trajectory prediction under road network constraints only based on massive crowdsourcing trajectory data and without any prior knowledge about the road network. We propose a deep learning-based trajectory prediction method based on LSTM model. We extract the road segment information from large-scale crowdsourcing trajectory data and annotate the position sequence of the original trajectories with road segment polygons. In this way, we translate the original trajectory into a road segment sequence. We also analyze the useful features and select movement, direction, and shape type jointly union with the road segment sequence as the input of LSTM model. Experiments on a real-world dataset show our method outperforms the network constraint trajectory prediction approach based on frequent pattern meaning algorithm. This is all I want to talk about. Thank you all for listening.
Hello, my friends. My name is Junyue Qin. I come from Anhui University. Next, it will introduce my paper, Distribute Vector Color Particle Filter for Target Tracking in Camera Network. The presentation is divided into 4 parts. Background, related work, DCPF, experiment. First of all, background. Particle filter is based on monocolor methods. It uses particle size to represent probability, and it can be used in any form of status space model. The advantage of particle filter technology in non-linear and non-Gaussian systems determine its wide application range. For example, particle filter is widely used in target tracking. As you can see below, the particles are in the blue region. The particle will follow the target as it moves. Particle filter has a good effect by using a single video to track the target. However, we need to combine multiple videos with color features to get a better tracking effect. It has the following 2 disadvantages when particle filter uses video to track targets. 1. Limit field of view. 2. Target occlude. The figure depicts a sense of application for tracking people in the camera networks. Although some cameras do not observe the target, which can also obtain the estimated state of the target by the distributed algorithm. The relevant work sessions are distributed below. At present, some papers have mentioned the distributed particle filter algorithm, such as 1. A distributed particle filter for bearings only tracking on spherical surface. The distributed particle filter combines the angle feature to track the target. 2. Correlation particle filter for visual tracking. The correlation filter combined with the particle filter analyze a single video to track the target. 3. Distributed multi-target tracking and data association in vision networks. The line-distributed target tracking method uses multiple videos to track multiple targets. These are just a few of the papers I have read. Here are just a few that are particularly relevant. In fact, before I read this paper, I read a lot of papers that are not very relevant, and I didn't get any inspiration from them. But it's not a waste of time, just like editing experiment. It's not useless. After reading a large number of iterations, I found a phenomenon that articles do not have to be read much, but must be read carefully. It is better to reproduce the experiment of the paper, so that you can better understand what you want to understand, and bring you more inspiration. Next, I will introduce the algorithm proposed in this paper. The framework of this paper consists of a local file filter and a fusion filter. The local filter is responsible for collect and process data and hand the data to the fusion filter. First, I introduce the local filter. The local filter is similar to the standard particle filter, except that the color histogram is added. Let's look at the model of the local filter, where Xmin, Xmax, Ymin, Ymax are the minimum and maximum values on the X and Y axis of a frame. RGB represents the color channel of a frame respectively, and hit bin is the size of the bin on each channel. Hit is the color histogram. Each node has a local file filter. The position of a particle needs to be continually converted back and forth between the position in the picture and the position in the reward, so as to meet the constant update of the particle and the interaction with the refueling filter. And the position convention of particles requires the convention matrix. Whether the image to the real or the real to the future, the convention matrix can be derived from the position of the camera. The main process of the liquefied are 1. Initialize the particle and histograms. 2. According to the proposition Q, propagation particles. 3. Use the measurement Z to update the weight. 4. Compute the UVPR. These are the main functions of the local filter. After the local filter completes its task, that will be the time of the fusion file filter. The steps of the fusion filter are similar to the local filter, including initialize, propagation, weight update, and mean calculation. Only the update of the weight of fusion filter is calculated by the local filter, and the specific calculation is shown in the equation. Equation 15 and equation 16 use the consensus algorithm. Equation 17 is used to get the weight of the fusion filter particles. And finally, we get the location of the target estimated by the fusion filter. The whole algorithm flow is shown in the figure. The algorithm fully shows the cooperation between local filter and the fusion filter, and then interactively works out the target position. The algorithm is modified according to the algorithm of others, modified to meet my own requirements of the algorithm. The equation used in this paper have been derived and proved by others. See others' excellent algorithm, knowing my lack of knowledge. The last one is the experiment part. These four pictures are scenes from scene 1. It can be seen from the figure that sometimes a camera will lose sight of a target, and sometimes the target will be blocked by obstacles. What we need to do is to use the camera with a field of view to find the target. Figure A particles is 500, hit being 8, relatively is 12, different color coefficient alpha, are of different method. Figure B, hit being 8, alpha is 0. DTPF CPF represent the error of particle is 500, repeated running 10 times with different iteration. DCPF1, CPF1 represent the error of particles is 300, repeated running 10 times with different iterations. Single camera selects the trajectory with the smallest error. Figure C. The curves of different color represent the trajectory of a target in real-world coordinates, which based on different algorithms. It can be seen from the figure A, B, C that the method proposed in this paper still has a good effect under various conditions. Scenario 2. The target is always within the field of view of the camera, but the target will be occluded. Figure D, E, F is similar to A, B, C. The results show that the proposed algorithm can be applied to many complex sensing, as shown in Figure A-D. Under the condition of different color coefficient alpha, DTPF has always maintained a low error, while the single camera is greatly affected. The number of TCF iterations is 12, the number of network nodes is 4, and the result has converged. So the error of DTPF is close to CPF. As shown in Figure B, E, under the same conditions, the errors of DTPF are similar to CPF. The error among different particle number is small. DTPF is stable when the number of particles is 500. When the number of particle is 300, the DTPF algorithm is relatively unstable and error-prone. It can be seen from the figure CF that the single camera is easily affected by the environment, while the DTPF still maintains good performance. The curves of different color represent the trajectory of the targets in real-world coordinates, which based on different algorithms, DCPF can keep consistent with the real trajectory in most alpha and the environment, while the single camera algorithm needs to the optimal alpha and the specific environment to keep consistent with the real trajectory. It can be seen from the figure that the DCPF can keep stable, and have small errors in various camera networks environment. Thank you.
Hello everyone, my name is Gao Kaihai. I come from Hefei University of Technology, and today I will introduce this paper, Hidden Micro-Model-Based Traffic State Prediction and Adaptive Routing Method in VNFs. It is divided into 4 parts to introduce this paper. The first is introduction, which will explain the background of the paper. Next, I will introduce the network module of the paper and some methods used, which should be the most important part. Then, there is the presentation and evaluation of simulation results. Finally, is a summary of the entire paper. With the rapid development of communication technologies, VNets have become an important component of the intelligent transportation system and played a very important role in many fields. The main characteristic of VNets are high mobility and unstable, because the vehicle moves at high speed on the road and changes direction frequently, which will cause communication link disconnect and information loss. In order to better establish V2V communication, routing algorithms are divided into 2 types: position-based and topology-based. Topology-based routing schemes generally require additional node topology information during the path selection process. Geographic routing uses neighbor location information to perform the packet forwarding. Due to the increase in the number of vehicles, route traffic studies is becoming more and more complex and time-varying. For better V2V communication, it is necessary to conduct route traffic studies and choose the appropriate routing method. So this paper proposes a new method to solve this problem. We mainly solved 3 problems in this paper. The first, how to get accurate observations. Second, how to get the road traffic studies. Third, what methods are used to face different road traffic conditions. Before that, let me introduce our network model. The basic network model is shown in the figure. Multi-line on-directional traffic flow is considered. The road between 2 adjacent intersections is considered a road segment, which is assumed to be much longer than the transmission range. All vehicles will move along the prescribed road and will not exceed the speed. Special public buses move on fixed routes. Other types of vehicles move along the roads at its own will. Each vehicle is able to acquire its own instant state on the basis of embedded GPS. The state of vehicle constitutes a 5-tube ID VAPT, representing the vehicle identification, velocity, acceleration, position, and time step. When the distance between 2 vehicles is less than their transmission range, they will communicate with each other. In the case where there is an obstacle, the communication is not possible. Therefore, vehicles on different routes cannot communicate with each other. Next, the first question: how to get accurate observations? Since we are aware that GPS may cause measurement errors and affect the judgment of road traffic schedules, Kalman filter is used to estimate the observation, which makes observations more accurate. Kalman filter is an effective recursive filter that estimates the state of a linear dynamic system from a series of noisy measurements. The Kalman filter uses two equations, the process equation and the measurement equation. This is process equation, where F is a state transition matrix, C is the system input matrix, and omega t is the process noise, which Gaussian distribution with zero mean and a covariance matrix Q. This is the measurement equation, where Zt is a measurement vector at time t, and H is a measurement matrix. Mu t is a measurement noise, which is a Gaussian distribution with zero mean and a covariance matrix R. The value we get according to Kalman filter is shown in the figure. It can be clearly seen that the estimation based on Kalman filter is more accurate than the predictive value. The error between the Kalman estimation and the true value is as low as 0.6 meter per second. Even if the increase in simulation time leads to an increase in the number of vehicles, the maximum error caused by the predictive value is 3.4 meter per second, which is much larger than Kalman estimation. It is effective for obtaining accurate observation to use Kalman filter. Next question: how to get the road traffic studies? 1. Divided the road into observation state and hidden state. 2. Use hidden micromodel to produce the hidden state of the road according to the observed state. In order to easily obtain the hidden micromodel, the road traffic state is divided into 3 hidden states: normal, rush hour, and accident. When the road is in a normal state, we consider that the vehicle can move at a high speed, and also consider the possibility of a slow speed due to the driver's behavior when there are few vehicles. When the road traffic state is at the rush hour, the number of vehicles on the road increases, which will cause road congestion with a high probability. The accident state is a traffic accident on the road. And observations are average speed, average acceleration, number of vehicles, and speed variance. According to the observation state we got, Whitby algorithm is used to accurately predict the sequence of hidden states. The first code of the Whitby algorithm is shown below. We know hidden micromodel parameters and observation sequence O. We can get the optimal path, which is the most likely hidden state sequence in HMM. The last question: what methods are used to face different road traffic conditions? In content with different problems in different road environments, when the road is in a normal state, it is necessary to find a suitable next hop node to transmit packet. When the road is in the rush hour, there are always vehicles within the transmission range. However, due to the slow speed and the larger number of vehicles, Frequently broadcast messages will cause scanner load and data loss. When a traffic accident occurs, images that should be transmitted first in order to restore traffic and reduce casualties. So we first distinguishing the route set and then choose the appropriate routing method. When the road is in a normal state, the vehicle is driving on the road at a high speed and the road is not congested. The target vehicle needs to find other. If no vehicle is found within the transmission range, the vehicle will carry the information for a period of time slot. During the time slot, if there is a suitable vehicle, the message will be transmitted, otherwise it will be discarded. When the road is in a rush hour, there are more vehicles on the road, which will cause road congestion. Due to the excessive number of vehicles and slow speeds on the road, frequently broadcast messages will cause heavy kernel load and severe packet loss. So, extended Kalman filter is used to predict the position of the vehicle and neighbor vehicles. EKF is extended Kalman filter, can be used to solve nonlinear problems. Individual vehicles' movement may be non-linear because of the complex road environment. We also set a time slot and broadcast every time slot in order to prevent the error of EKF estimation from being amplified. When an accident happens, it will introduce local congestion. Therefore, images that should be transmitted first. We will increase the problem of emergency information and extend the time to store packets in order to find a suitable next hop. Postal code for routing method selection is shown. According to the product route status, select a appropriate routing method to improve routing performance. Next, I will introduce our experiment and evaluation. We compare our routing method with the Hello protocol in AODV and Kalman production-based neighbor discover. The Hello message protocol in AODV is a typical way that uses fixed time interval to broadcast. KPND uses Kalman filter to predict the position of neighbor nodes. When the error is greater than the threshold, the neighbor table is refreshed through broadcaster. The simulation parameters are shown in the table. We contain the total number of packets generated during the whole simulation. Our method is called PHMM. The figure shows the number of packets generated during the simulation where the maximum speed is 30 meters per second. At the beginning of the simulation, because there are fewer vehicles, fewer data packets are sent and the road is not congested. PHMM, AODV, and KPND generate similar number of packets. When there are more vehicles, the state of the road traffic changes, and the data packets generated by PHMM are obviously less than AODV. As new vehicles continue entering the road, KPND needs to frequently send messages to refresh the neighbor table. So when the simulation time increases, the number of data packets sent is more than PHMM. From this figure, it can be observed that PHMM can send fewer packets compared with LODV and KPND in different maximum speeds. The lower the maximum speed, the easier the road becomes congested, and when the distance between vehicles becomes closer, it is easy to find relay nodes to transmit packets. So when the maximum speed is low, more data packets are sent. Therefore, when the maximum speed is 10 meters per second, the most number of packets are sent. And when the maximum speed is 30 meters per second, the last packets are sent. Finally, we compared the packet delivery rate of the three methods. The value of packet delivery ratio decreased with the increase of the sample time. When the number of vehicles nodes increases, the packet delivery ratio of LODV decreases faster than that of PHMM. With the PHMM, we can obtain larger packet delivery ratio than using LODV. During the whole simulation time, the packet delivery ratio of PHMM is about 5% higher than that of LODV on average. KPND shows a higher delivery ratio when there are few vehicles, but when there are more vehicles and the road traffic state changes, PHMM's delivery ratio is better than KPND. These comparisons show that PHMM is more adapted to the time-varying road environment. Finally, make a conclusion of this paper. In this paper, a routing method based on HMM is proposed to predict route schedules. We can use this observation to predict whether the vehicles on the road are driving normal, congested due to rush hours, or traffic accidents. In VANETs, to provide accurate information transmission and a fast interaction, must find a suitable routing algorithm. Choosing the right routing method by predicting road conditions is a new idea. Simulation results show that compared with LODV and KPND, our method increases the value of packet delivery ratio and decreases the number of packets in the changing road environment and reduces the channel load. Thank you very much.
Hello everyone, we come from North China University of Technology. We are honored to share our recent research here. In this paper, we proposed a model to predict traffic flow in highway domain. With the development of city, intercity highway plays a vital role in people's daily travel. The traffic flow on the highway network is also increasingly concerned by road manager and participants. It is difficult to construct a multidimensional feature matrix and predict the traffic flow of network at one time. We proposed a novel prediction method based on a hybrid deep learning model, which can learn multidimensional feature and predict network-wide traffic flow efficiently. Next, I will explain our work from 4 aspects: scenario, motivation, model, evaluation, and conclusion. Let's introduce the scenario in this paper. With the development of country, the connects between cities have become more convenient. People's work and life are inseparable from the intercity highway. During the update of road infrastructure and the increase in the number of vehicles, the traffic situation of highway has also been paid attention by city officers. In recent years, the rapid development of intelligent transport systems has brought new solutions to traffic management. By integrating and analyzing data generated by Internet of Things device, it can better provide suggestions and predictions. One of the most important functions intelligent transport system is traffic flow evaluation. It can help managers better detect road conditions and make reasonable plans. So many researchers are focusing on traffic flow prediction with different time and space scope. However, with the development of technology, lots of data in different types can be used, so there are still challenges in traffic flow prediction domain. With the development of IoT technology, types of data become diverse. This data can be more or less impact on the traffic flow. For example, the impact of extreme weather, such as heavy rain and fog, is obvious. For weekdays, in morning and evening peak, traffic flow is significantly higher than the noon. Therefore, how to explore the relationship between the data for traffic flow prediction has to be considered. At the same time, for the highway, it is a loop topology. Toll stations are related to distance. When a vehicle enters the highway, it is necessary to pass the adjacent segment. Therefore, in highway domain, the benefit for the traffic flow prediction in a whole network are more valuable than single one. So, how to collect the data and predict the network traffic flow at the same time is the focus of the research. Different data types will have different effects on the traffic flow prediction. The next challenge is model selection. With the development of machine learning, models have become diverse. However, shadow learning has no advantage in multidimensional feature learning. Deep learning can accomplish the goal more well. At the same time, higher prediction accuracy is our common goal. So, a fully convolutional network and cooperate with a non-short-term memory network is proposed as a hybrid deep learning model. It can fully learn the multidimensional features and predict the traffic flow of the whole network. In our daily practice, traffic flow prediction become a particle problem in highway domain. As an important function of the intelligent transportation system, traffic flow prediction have always been the focus. For example, highway big data analysis system can conduct business analysis by integrating toll station data. Through the intelligent equipment and other information collection system installed on the toll stations, we can get record when vehicle pass the toll station. toll station data reveals the traffic flow around it. When the road becomes congested, the toll station data in the highway network will increase. Therefore, toll station data is the basic for us to predict traffic flow. As we can see, the toll record has 3 parts of dimensions. In entity dimensions, we use the vehicle detail to identify the vehicle. In time dimensions, we can know the spatial-temporal attribute of a vehicle, like the time vehicle enter and access the highway. In space dimensions, we know the location information that the vehicle enter and access the highway network. We can aggregate each record to determine the traffic flow at each toll station. It is very important for network traffic flow prediction. Through the data cleaning process, we can get the complete trajectory of the vehicle in highway network, including the static information of the vehicle and the dynamic information that the vehicle passing through toll stations. Due to the urbanization, the traffic flow around main city is significantly larger than distant cities. Therefore, traffic flow prediction for key regional stations can't represent the network situation. If we can predict traffic flow of all the toll stations in network at one time, it will provide global strategy support for highway managers. There are another factors that will affect the traffic flow too. One is the weather. When the people are faced with heavy rain and fog, travel plans will be affected. It will lead to the fluctuation of traffic flow. Secondly, date type will also become the one of influencing factors from the daily analysis. The arrival of holidays will directly lead to a peak of travel, and the traffic flow of that day will increase than usual. Therefore, how to fully consider weather, date, and other influencing factors and find the correlation between data is the key issue of flow prediction. We choose the existing record as the basis data for the simulation of traffic flow because it is a completed record for the vehicle. In Chinese highway domain, only when the vehicle leaves toll station means tolls will be charged. After a completed record, we can still analyze the incoming information of the vehicle. Daily traffic flow is the main dimension for the prediction. But from elaborate observation, we found that other dimensions also affect the traffic flow of highway toll stations, like weather, date type, and related station traffic flow. This date type must be fully considered when modeling feature, so there is a definition of future modeling in media-logical features. The occurrence of extreme weather will affect the daily traffic flow of highway network. The raw weather data we have the property of weather condition, temperature, wind speed, and direction. When weather condition is heavy rain, fog, or the degree of wind is bigger than 6 level, daily traffic flow of toll station will drop, so we define it as extreme weather. In date feature, due to the holiday period, the highway network will adjust the charging mode, which leads to significant influence in traffic flow. Therefore, the date feature is also one of the important factors that affect the traffic flow. We define date features as holiday, weekday, and otherwise. In the last feature, we compute spatial relation traffic flow with toll station S. As we all know, highway network is a loop topology. The network traffic flow is influenced by all toll stations. For the toll station S, its adjacent stations' daily traffic flow is considered. The adjacent station means the tow station nearby S in spatial dimensions. The traffic flow of the adjacent station will influence the traffic flow of S. We calculate the Euclidean between each tow station. Take n nearest tow stations. The massive is composed of fully convolutional network and the long short-term memory network. As we can see, we propose to use convolutional network to fit multi-dimensional features. Then we use concatenation layer to retest the data into time series. Then let LSTM to learn it. Finally, we use linear layer to restore network traffic flow. This combination considers both spatial and temporal of multi-dimensional feature. Based on one relation to work, 3 stations with mini distance from the tow station S have the most obvious impact. So 3 adjacent stations, daily traffic flow was selected for future modeling, plus weather and date type factors, which constituted the 5-dimensional feature of each tow station. In order to learn the spatiality features, we choose to use spatial convolutional network. The tow station data of the highway network has both spatial and temporal dimension, and it is not enough to only consider the spatiality. Therefore, after the convolutional network, we add a concatenation layer to construct a time series and input into LSTM network to learn temporal feature. Finally, a network traffic flow prediction method is formed through hyper deep learning architecture to make prediction. The following is the detailed description of each component. For future modeling, we built network tow station future matrix for all tow stations in network. This matrix is composed of all tow stations and the multi-dimensional future vector of each station. It contains spatial correlation feature and other dimension features that affect the traffic flow, like weather and date type. First, we use convolutional neural network for future learning. Convolutional neural network was first used in the field of image recognition. Through the calculate of pixel and convolutional kernels, it learns the relationship of each pixel to achieve the role. For the input, we choose hetero-convolution kernel to calculate. Usually, the pixels of the image are irregularly disputed. We already considered the spatial dimension in multi-dimensional future vector. There is no need to compute each station correlation on it. Therefore, we designed a hetero-convolution kernel form, only compute the gloom direction of the future matrix. First, we designed a set of kernels to calculate with the matrix. Second, we uniformly perform polling operations on the channel. We use cross-channel polling to reduce channel dimension. Our polling method only average channels, which we call channel subsampling, to achieve the purpose of channel dimension reduction, so that we can retain the feature matrix structure in one channel. The output is the prediction value of traffic flow for each station in highway network. We use really daily traffic flow as training label to training the network we designed. After training, we get daily traffic flow matrix on each day. After getting the daily traffic matrix of all toll stations in network, in order to use temporal of data, we will process the material in concatenation layer into time series. So after concatenation layer, we can get time series data as input. Then we choose long short-term memory network for future learning in time dimension. LSTM network is an improved model of recurrent neural network. The classic long short-term memory cell block contains 4 components, namely input gate, forget gate, output gate, and cell state. These 4 components together make LSTM cell block have memory and function of learning time dimensions. By serializing the future matrix of toll station in whole network, long short-term memory network can also learn the time dimension features of data and improve the prediction accuracy. We put the time series data generated by the concatenation layer as input into long short-term memory network. We use 15 days future matrix for training and use daily traffic flow of the next day as the label for learning. Finally, we get the predict value as traffic flow of all toll stations in highway network. The combination of the above 2 deep learning model has fully studied the spatial-temporal and multidimensional feature of the data. At the same time, through the improvement of the convolution network, the method can predict the highway network traffic flow at one time. The experiment used real data from the toll stations of highway network. The open-source deep learning framework TensorFlow supports the construction of this model. We named our method as hybrid deep learning method to compare with 4 machine learning models. Then we choose 3 predictive metrics to evaluate the method. We designed 2 experiments for method evaluation. The first is comparative experiment to verify the effectiveness and the accuracy of HTM by comparing with other methods. Secondly, we use HTM to predict all toll station traffic flow one time and compare with traditional long short-term memory network prediction method. First, we randomly select Zhengzhounan toll station for analyze. We can intuitively see that the HDM fits the real value best and has good performance in the time period of wave peak and wave trough. At the same time, the fluctuation of GBRT is worse than HDM. Although the overall trace is close to the true value, the prediction of the turning point is lacking. Compared with the SVR and ARIMA models, our method's prediction is more accurate, and like the KNN model, it can fit the real curve well. In this experiment, we use HDM to predict network traffic flow at once, and use normal LSTM model to predict traffic flow for comparison. We choose 4 toll stations for experiment. Their daily traffic flow is different. The single toll station prediction uses the same training set and use LSTM neural network model for time series data learning. We can see the prediction performance of HDM is better than single station traffic flow prediction. The network traffic flow prediction method is fully verified, and the expected prediction effect can be achieved. In this paper, we proposed a new multi-dimensional future-based network traffic flow prediction method. A hybrid deep learning model consists of a fully convolutional neural network and a long short-term memory neural network is proposed. It can fully study the spatial temporal of highway toll station data. We considered the spatial feature of data, and some other features can affect traffic flow like weather and the date type. We use this for future modeling. After learning this toll station future matrix, the method can well predict the traffic flow of highway network. Experiments show that the method has good performance compared with the shadow machine learning method. At the same time, it has a good effect on the learning of multi-dimensional feature. In the future research, we would subdivide the dimension of features and consider more relationship between the traffic flow. We can also improve the performance of neural network in deep to predict more precise. The above is all the content of our work. I'm very happy to share with you here. If you have any question or suggestion, please email us.
Hello everyone, I'm Yihan Zhao, come from Xi'an Jiaotong University. Next, I will present our work, HomoNet, Unified License Plate Detection and Recognition in Complex Sense. This is the outline of today's presentation. First, I would like to introduce the background of this work. China is a country with a large car production. Every year, car violations occur frequently, such as illegal parking, vehicle compaction lines, and so on. This gives pressure to the traffic department and also brings chaos to traffic. And it's a heavy task to check this by manpower. Therefore, it's meaningful to use deep learning technology to dig out the information. With the development of deep learning, license plate detection and recognition has been widely applied in our life, such as intelligent transportation, parking, toll station, and so on. In this scenario, the high accuracy and fast speed must be realized at the same time. Besides, cars run at high speeds in different directions in complex situations, causing the license plate may not face the camera, making it to be twisted, rotated, perspective, and distorted. And it also posing a challenge to LPDR. Many researchers have worked to improve performance in recent years. Most systems divided the LPDR into two independent parts: license plate detection and license plate recognition. These methods have three limitations. The first, the detection result is a bounding box that can only use 2 points to locate the license plate position. The second, the neural network is difficult to recognize rotated characters. The bounding box only can crop the region of LP, but ignoring its perspective change because of the direction to the camera. Thus, methods lacking correction cannot efficiently solve the problem, which the license plate is twisted in complex sense. The third, the two subtasks cannot train end-to-end jointly and spend more time on the process. Another way, the method of LPD mainly draws on the mode in object detection. All these methods are suitable for multi-targets with different sizes in one image, so they need to design different anchors to match the corresponding target. Inspired from text spotting, a fine transformation was introduced to solve the problem of license plate distortion. A fine transformation is equivalent to posit 3 coordinates in the original picture. Determine the transformation matrix and then rectifying the license plate. This method can only improve the recognition problem of perspective character to some extent, but cannot solve it. For example, as is shown in figure 1b, compared to 1a, Character 9 is recognized, benefiting from the transformation, but character 3 is still difficult to identify due to the detection error of the upper left corner. In this paper, based on perspective transformation, a unified network with HomoPoling operation was proposed, as is shown in Figure 1c. Even if there is an error point, 4 points can still extract all valid information and correct the twisted license plate to improve the accuracy of the recognition. Moreover, HomoNet puts the detection, rectification, and recognition into one network to ensure end-to-end training, so it can improve the efficiency and accuracy. The whole framework is shown in this figure. The first part is the key point detection mode. When getting the license plate key points, it can apply them to the perspective transformation to correct the license plate to the horizontal direction, which is easier to recognize. The second part is HomoPoling. HomoPoling can do the same thing, but it can be end-to-end trained. The last part is the recognition mode, which using CNN and max polling to encode text information, and we use CTC decode the final results. As is shown in this figure, license plate key point mode adopts the structure whose backbone is ResNet and FPN. Firstly, this mode links multi-level features from the input image. Only the fourth level of FPN is used to extract the feature maps. Then, we use group normalization and the activity function referred to the paper. Finally, one convolution is applied to output 5 canal key points heat map. The first 4 canals predict the probability of every pix being the key point, whose order is left top, right bottom, and left bottom. The last canal is background heat map. The heat map is set to 1 at the position of lines corner, and 0 at some other position in the first 4 canals, while the label is the opposite on the canal 5. The loss function is binary cross entropy with logits loss, which can be formulated as follows. HomoPoling sample the errors determined by 4 key points to align the distorted license plate to the horizontal direction. It consists of 3 steps. The first step is to get the homographic matrix. The second step is to generate the sample grid. The final step is to produce the rectified image through sample from the source grids. License plate recognition mode aims at predicting a character sequence from the rectified image transformed by HomoPoling. Because the length of license plate numbers is different in some errors, so we choose CTC decoder. What's more, the CTC decoder reduces the computation and the speed. The AOLP, CCPD, and BGY datasets were used to verify the proposed mode. To compare with other research, AC and LE in AOLP was considered as training set in this article. What's more, to improve the robustness of the HomoNet, the experiment involves the date augment during training, and there are not any synthetic data. For different datasets, the input size is changed, as given in this table. This figure shows some of the experiment results trained using our key points mode on AOLP. It can be seen that this mode can detect the key points of the license plate even in the dark, strong light, rotation, and other conditions. Although some key points have errors, the 4 key points can still contain the whole license plate information. This figure shows the correction results after the homopolling. It can be seen that prospectively, rotated and distorted license plate are corrected to the horizontal direction. As is shown in this table, our method achieved the highest performance, 0.6% higher and 18.6 milliseconds faster than the state-of-the-art method. Benefited from rectifying the license plate by homopolling with the 4 points information, and one car has only one license plate. We convert the license plate detection into license plate key point detection, which is without anchors and NMS. So our mode achieves the best precision and speed. This figure shows some of the experiment results on CCPD. It can be seen that this mode can effectively detect the key points of the license plate even in different sense. This figure shows the correction results after the homopolling. It can be seen that the license plates, which is perspective, rotated, and distorted, are corrected to the horizontal direction. In this table, HomoNet achieves the best results on all subsets except dB. Benefited from homopolling, our mode achieves a large improvement in rotate, tilt, and weather, which is 4.4%, 4.5%, and 9.6% respectively. This figure shows some of the experimental results on BGY. It also shows good results. As is shown in this table, we obtain a detection accuracy of 52% and an end-to-end recognition accuracy of 91.33% on the BGY dataset. This proves that HomoNet can not only correct, but also can recognize license plate with multi-taps and different character lengths. In our paper, a fast unified network, HomoNet, that contains homopolling based on perspective transformation was proposed. Homopolling can get more information and rectify the oriented license plates. And an end-to-end network is designed. license plate detection, license plate correction, and license plate recognition is integrated into a unified network structure through the HomoNet. In the future, the proposed method will extend to the double LAN license plate to be trained in this framework. Another way, we plan to explore the representations of fuzzy license plates for vehicle re-identification. So that's my presentation. Thanks for your attention.
Hello everyone, this is Qinglan Peng from Chongqing University. Nice to meet you guys in cyberspace. I'm glad to share our recent studies on reactive workflow scheduling problem. It's a deep reinforcement learning-based approach. Let's first review the cloud-based workflow scheduling problem. As we all know, workflow is a useful process modeling tool. It has been widely used in our daily lives to construct computation-intensive applications such as scientific computing and big data processing. Cloud computing is a promising computing paradigm. It features like elastic scaling, unlimited resources, on-demand instances, and pay-as-you-go billing modes make it an ideal platform to support computation-intensive applications. Well, this study targets at the workflow scheduling algorithm that's designed for the workflow service provider. As shown in below figure, end users submit workflow jobs to workflow service provider. The service provider acquires computing resources from the IaaS providers and executes these submitted jobs from the end users to get income. Thus, for workflow service providers, how to schedule workflow properly to satisfy users' deadline constraints and minimize the virtual machine hiring costs is their ultimate goal. Existing studies on cloud-based workflow scheduling can be classified into two categories. The first is static scheduling approach. The other is reactive scheduling approach. This figure compares the differences between these two kinds of approaches. It can be seen that in static scheduling approach, the scheduling decisions for tasks in a workflow are made together after workflow requests arrive. This kind of approach can yield high-quality schedulers. However, it makes time to do such a global optimization. While in reactive scheduling approach, task scheduling decisions are made only when they are ready to be executed. This kind of approach can make a quick response to the change of the outside environment. However, its task-level view that it suffers from low cost efficiency. Well, after a careful review of existing studies, we found the limitations of them lies in three folds. First, most of them assume that the virtual machine had from us providers have steady performance. However, in real-world application scenarios, their performance fluctuates all the time. Second, the traditional static scheduling method suffers from the searching space explosion problem when faced with massive workflow requests and huge resource pool. Thirdly, as mentioned earlier, the task-level view of some reactive scheduling approaches may lead to low-quality schedulers. Well, in our proposed method, we consider fluctuate virtual machine performance. We formulate the reactive workflow scheduling problem into a continuous decision-making process and propose a deep reinforcement learning-based method to solve it. We first introduce our system model. As shown in below example, we use a DAG to represent a workflow, where T is the set of the tasks, E is the data dependencies between tasks, and D is the user-defined deadline. We can also learn from the figure that tasks have different execution time on different types of VMs, since they have different performances and prices. As shown in equation 1, given the price of different types of VMs and the scheduling plan of a workflow, we can calculate the cost of hiring VMs to finish the workflow. Here we use M to denote the actual execution of a workflow. Note that if M exceeds the deadline constraint D, additional penalty will be incurred to the final cost. Now we can give the definition of the problem to be addressed. It can be seen that our goal is to minimize the VM hiring cost while satisfying the user-defined deadline constraint. This is a textual, continuous decision-making process, and there are no online algorithms that can get the optimal solution. In this paper, we formulate the above proposed problem to a Markov decision process and using deep reinforcement learning method to solve it. The below figure shows the process of deep reinforcement learning. It can be seen that its target is to train a strategy pi to help us make proper decisions under different states. We first give some basic definitions of the proposed MDP problem. In our approach, the state is defined to the status of the whole system when a task is ready to be executed. As shown in this figure, there are 4 tasks in a workflow, thus it has 4 states. In this paper, we define the observations to the status of the whole system at a certain state. It's just like a snapshot of the whole system at a certain time point. We use a L+5 tube to represent it, where L is the number of the VM types available for workflow service provider. And we also define the action of the workflow scheduler to a types of VMs that a task should be scheduled to. Reward function is the key to design a reinforcement learning method. It represents what kind of scheduling strategy we want the agent to learn. Equation 2 shows the reward function used in our approach, and the below figure shows its reward distribution. Here we use F to denote the earliest computation of a workflow. Suppose we have 2 scheduling police, A and B. For a given workflow, their finish time are FA and FB respectively. Clearly, both FA and FB satisfies user-defined deadline constraints because FA is greater than FB. We said that policy A is better than policy B because the policy A can reduce the cost by hiring slow but cheap virtual machines. To train scheduling models, we also design an environment evaluator to simulate the process of reactive workflow schedulings. We implement these emulators by Python, and we consider multiple factors such as pay-as-you-go billing modes, fluctuate virtual machine performance, and virtual machine acquiring and releasing delay. We employ a deep queue network to map states to the probabilities of different actions. The input of our neural network is the observation of current system, and the output of it is the probability of different actions. For more our DQN design and parameter setting details, please refer to our paper. In our experiment, we consider 4 kinds of real-world scientific workflow templates from Pixel's project kit. We also consider 5 types of virtual machine configurations from Amazon EC2 and use a normal distribution to simulate its performance fluctuation in runtime. We consider 1 reactive method and 2 static methods as baselines to conduct our experiment. We first evaluate the deadline hit rates of our proposed method and its peers. As shown in these tables, in most of cases, our proposed approach, short for DWS, can get the highest deadline hit rate. Note that here we use alpha to denote the deadline constraint level, where alpha equals 0.2 means that deadline constraint is tight, while alpha equals 0.8 means that deadline constraint is loose. We then evaluate the cost incurred by different methods. It's also clear that our proposed DWS method achieves the lowest cost in all cases. So here comes the problems. Where comes the gain? We also take a further analysis. The above figure shows the execution pace of different approaches, and the below figure shows the proportion of different types of virtual machine held by different approaches. We can find that the proposed DWS method can control the pace of execution of the workflow, just like the static method PSO did. That PSO has the global views of the whole workflow. Besides, it also tends to help cheap virtual machines to achieve cost-effective schedulers while meeting the deadline constraints. Okay, to sum up, in this paper we target at the reactive workflow scheduling problems. We consider the fluctuate virtual machine performance during the runtime and propose a deep reinforcement learning-based approach. In our future studies, we plan to employ some data mining method to achieve a predictive scheduling. And we also gonna to consider both on-demand and on-spot virtual machines to build our resource pool. Okay, that's all. This is my email, and please feel free to contact me if you have any question.
Hello everyone. Today I will give my presentation. The title is EPA, the optimal placement of interdependent VNFs in many core sectors. I'm come from Information Engineering of Engineering Institute of CS. My research is about computer network architecture and fifth generation. I also interested in network security. First, I will give the introduction. As well know, the object of NVA is to run SFS on commercial servers. Besides, it also brings flexibility for the distribution of network service. It also reduces overall hardware cost. And in the current stage, most of the studies focus on the placement of SFSAS. Almost all of the research treat each server as an entire node. That to say, all cars in the server are equal in the allocation of various NFS. However, CPU-based metacores usually adopt NUMA architectures. That to say, CPU cores are partitioned into several nodes, and the performance of cross-load and inter-load is significantly different. For example, there is 6 NF, and each NF has different computation units. We assume that the sequence is NF1, NF2, NF2, and then to the lot NF6. And we can say that each node there are two nodes, remote nodes and local node. Each node has memory and LSA cache. And from the third page, we can say that they have closed the QPR, but for 3 times, but the latter page, we can say that there I will close the QPR, but there are only 2 paths. Of course, the latter path, the performance of the latter path is better than the third page. So we can say that more specific considerations are required for the interdependent VNF placement in medical sector problem. Means I will PMS in my paper. In this paper, I consider the dependency relation between NFs, and I also consider the NUMA architecture. I also consider the effect of NUMA architecture to the performance. In my paper, all main research is studying the placement of SFS within a server. We consider the integrity of CPU cores in different nodes. We also consider the different types of NFS dependency relation. Second, I will give the problem formulation and analysis. It gives the following definition. For the array, assume a set of loads V with C equals and a set of SFS is denoted as S. Let f is be the S when F, and we introduce a symbol to describe the dependency relation and define a function, namely PSIK, to denote whether NFI of trace S is located in the load key. If the function is equal to 1, let's say the NF of trace is placed on load key. Otherwise, it is equal to 0. We also define phi aspect. It means it is the most optimal performance when the whole SFC collocates on the same load. And then we define phi S, the attenuation performance when NFS of the same FFS collocate across loads. We also define phi J. It is a correlation index between phi S beta and phi S, and they have the following relation. Then we need to analyze the formulation. As we can say that if we want to solve the formulation, the critical parameter is phi J, but it is hard to solve. It is hard to find the result of phi J. So we assume Pi. So we introduce other parameters here. We assume Pi and Mi denote the ideal performance and the metric value of NFI. And here we adopt mathematical Pearson correlation coefficient to compute the correlation. Then we can deduce that the function of phi J should be consistent with the following function in form. Where alpha I and Mi and alpha J, Mj are the performance of F curve I and J. Alpha I and alpha J are the coefficients. However, we can say that we cannot use limited technology as the import directly to expound the effect of interdependent NFS. So we introduce another metric value, namely resource stores. And phi J is and from this observation, we can approximately formulate this function as as the following equation. Of course, they are subjected to the second equation and third equation. The second equation and the third equation. The second, and of course, they are subjected to the second equation and the third equation, where alpha and beta are tuning parameters to the aggregate effect of closed load placement of interdependent NF curves. Then we will give our algorithm, namely backtracking placement of algorithm. After analysis, we can say that the equation is the time complexity of the above equation is OKC. K is the number of available loads and C is the number of total NFs. And we can also let it is NP hard. Therefore, we can not find the polynomial time approximation algorithm to find an optimal placement. As a result, we propose a heuristic backtracking placement algorithm, namely BPA. The basic idea behind our heuristic algorithm is to place all of NF curves in the same load as possible by minimizing the number of remote access across loads. We should offer NFs in the same SFC as entirely and place all entitled train on the same load. Then we move NFs selectively to remote load due to resource constraints. At first, we search NFs that have nothing to do with the position in train and remove them to remote loads. Then we remove NF curves at the end of train to remote loads. Here, there is the algorithm. Then we give the performance evaluation. In this paper, we use a high-performance NFV platform, namely OpenLight VM, and we chose 4 types of NF, namely IPv4, router, firewall, DPI, and switch. The import traffic is generated by the DDK packet generator tool. Before proceeding with our evaluation, we need to measure the metric value of EF and FF to facilitate the computation of 5G. We assume that there is a dependency relation between each other. The first page is the metric value for NFs. We can say that the various slightly. And the second page is the maximum values of amber cups. We can select the average correlation index. The average correlation index for different cup is differently balanced way. We can reduce the search time enormously. We can reduce the search time enormously. To demonstrate that all heuristic algorithms can improve the aggregate performance, we compare it with greedy placement. Greedy placement collocates the NFS on the local load in priority until you sort the course. In this paper, each core play one NF. Just play one NF. We also compare it with Fanny's placement. Fanny's placement tempers poor place SFSA as on the all loads in sequence. That page shows the normalized performance of above placement algorithm. So we can select in all SFC sets, all algorithms can achieve the better aggregate performance among the placement strategies. We also evaluate the effectiveness of our algorithm. We compare the backtracking placement algorithm with the brute force method. We randomly select two sets from above SFC sets as input and increase the number of placed SFC gradually. Let's big shoot letter. It can find a solution in less than 2 seconds. Even in the vertical case with 5 SFs, comparing with the brute force search strategy, it can reduce the time to find the near optimal placement tremendously. At last, I will give a summary. In this paper, we studied the SFCS placement in medical system to improve the aggregate performance. First, we formulate it with the NILP model. Then we find a reasonable measure to weigh the effectiveness of NF cup. Then we present a heuristic-based backtracking placement algorithm. At last, the evaluation should let BPA can improve the aggregate performance. That's all. That is my presentation. Thank you.
Hello everyone, I'm honored to have the chance to address you on this special occasion. The topic of my paper is cooperative source-seeking in Scalar field, a virtual structure-based spatial-temporal method. The outline of my talk is as follows. The first part I want to introduce is the background of this research. The second part is the related works. The third part covers the method proposed in this research. And then we introduce the empirical results. Finally, a simple conclusion is given. Let's move to the first part of this topic. The background of this work is like this. I'm going to introduce the background of this study. In the last decade, cooperative source-seeking based on multi-agents have been drawing more and more attention and widely used in many fields, such as agricultural irrigation, oil spill monitoring, environmental monitoring, and first response search and rescue tasks, etc. For example, when looking for a missing backpacker with a positioning signal device in the wild, in the face of complex terrain conditions, drones and unmanned vehicles can be used to perform search and rescue missions. Multi-robots cooperatively searching for signal source can also improve the efficiency of source-seeking. Gradient method is a good way to solve the source-seeking problem. There are various approaches to deal with this topic in the current literature. For example, several source-seeking algorithms are based on gradient descent method. If it is available, the gradient of the signal field can be used to produce a gradient descent algorithm for a vehicle or group of vehicles. However, in practice, the agents are only capable of measuring the signal strength, and the gradient information is usually unknown. In this situation, the gradient can be approximated using spatially distributed measurement of the signal distribution. Gradient-based methods are also widely considered in source-seeking applications, which can mainly be divided into single-agent method and multi-agent cooperative method. As for single-agent, researchers use random gradient estimation to make the agent randomly move in the signal field, measure the spatial information of the signal field, and calculate the gradient direction to move to the source. As for the single agent, researchers use random gradient estimation to make the agents randomly move in the signal field, measure the spatial information of the field, and calculate the gradient direction to move to the signal source. Some researchers made a single agent calculate the gradient by random movement and drove the agent to signal source with gradient information. The other option consists in multiple vehicles collaborating to correct concentration measurement at multiple locations to calculate the gradient. Some researchers propose a circular formation method, which enables the team to maintain uniformly distributed circular formation, with which means the agent calculate the gradient and drive themselves to signal source. In this section, I will introduce virtual structure-based method with fusion of spatial and temporal information collected by the robot team. The agent moves along the gradient ascendant direction of the signal field and finally reach the position of the signal source. the scalar signal field is unknown, and the distribution of this field is related to the distance from the source. The closer you are to the source, the greater the signal strength. The farther you are from the source, the lower the signal strength. In this section, we detail the proposed signal source thinking method, which combine the spatial and temporal information of the signal field. The method is divided into two parts. The first part is about how to use spatial information of the signal field. The second part is about how to use the temporal information of the gradient. We firstly give a brief introduction to the circular formation-based method, so as to utilize the spatial distribution of the signal field. Then we fuse the temporal information of the signal field by sequential gradient information. Finally, we recursively perform the above steps, calculating the direction of the gradient until we find the source. And in this part, I will introduce corrective gradient estimation. I introduce how the circular formation of multiple robots use the spatial information. In order to explore the spatial information in the field for gradient estimation, we use the algorithm in previous study, in which the robot team maintain a uniform symmetrical circular formation to calculate the gradient. And in order to use the spatial information, these robots are completely evenly distributed on a circle. The most direct result is that the sum of the factor from the center of the circle to each robot is a zero factor, which means we could make use of the spatial information to estimate the gradient with the individual measurement of each robot. I will explain later. And the signal strength measured by each robot at different locations is different. We can know from the content mentioned above. And in these equations, if we omit J of P on the left side of the equal sign, we will get a zero vector, because the sum of the vector from the center of the circle to each robot is a zero vector. And if we multiply each vector with the signal strength measured by respective robots, which is J of P, and then add this vector together, like this equation does, we can get an approximate gradient vector, which is nabla J of C. This gradient vector will point to the direction in which the signal strength increase in the area where these four robots are located. When we add JP on the left side of the equal sign, the right side of the equal sign will get an approximate gradient nabla of C. In order to integrate the time sequence information of the signal gradient and make the robot team to find the signal source in the shortest distance with higher efficiency, the gradient is obtained by averaging the gradient in the target location CK and a nearby point CK subtract. The shaded area is the robot's field of view. As the robot team moves to the target location CK, The target location CK enters the vision of the robot team, and on the straight line between the current position and the target position CK, take the point CK plus CK subtract with the distance d from the target position, and the robot team calculate the gradient when passing through this point CK subtract. When the robot team arrives at the target location CK, the gradient is calculated, and the above two gradients are merged, which can be used as the gradient JGK of the target location in next step. The robot team keep repeating the process described above, constantly producing a series of CK subtract and CK points, and constantly moving to the position of the signal source until the signal source is found. In this section, we introduce the experimental results. The first experiment is a typical trajectory experiment. On the same signal field and the same starting point, we compare the method we propose with the other two state-of-art methods. A group of robot team or single robot with different methods search for signal source. The two comparative methods are more easily affected by the signal noise, as the trajectory fluctuated more heavily and are more tortuous. In contrast, the trajectory curve obtained by the method we propose, the red one, is smoother and simpler, which implicit our approach is more efficient and robust to variance-changing signal. The method proposed in this paper reduced the interference of noise on the gradient calculation and made the trajectory more consistent with the direction of gradient increase in the signal field. This shows our proposed virtual structure-based method has better stability and anti-noise characteristic. We conduct 100 experiments on the robot of the three methods in the same experimental scenario, and then record the change in distance from the source with the number of iteration steps. We can see that the efficiency and the stability of the method proposed in this article are significantly better than the other method. We also count the cumulative distance of different methods under Gaussian noise with different variances. We mark the error bar of the cumulative distance on the graph. In the figure, we can also see that the method in this article is more robust to noise interference. And compared with the other two methods, our proposed method enables to find signal source with the smaller iteration steps and cumulative distance, which can effectively reduce the task overhead and improve the efficiency. Thank you.
Hello everyone, my name is Wang Gongju. I will be the reporter today. My report topic is BiC-DDPG, Bidirectionally-Coordinated Nets for Deep Multi-Agent Reinforced Learning. This work was supported by the Artificial Intelligence Research Center, National Innovation Institute of Defense Technology, Tianjin Artificial Intelligence Innovation Center, and the College of Computer National University of Defense Technology. The arrangement of my display content is as follows. First, introduction of my work, then the related work and preliminary. Next, I'd like to introduce our algorithm Bidirectionally-Coordinated Deep Deterministic Policy Gradient. After that, I'd like to introduce you the experiments of my work, then the results and the discussion. Finally, the conclusion. The keywords of my work is multi-agent deep reinforced learning, large discrete joint action space, cooperative mapping method. First, I'd like to introduce the background, then the scenarios. Next, the challenge of the multi-agent. About the background, multi-agent problems appear commonly in computer science and robotics. It is a hot issue both in the academic and industrial. A series of algorithms has been formed, such as HomoNet and BiC-DDPG. Deep neural networks and multi-agent reinforced learning provide new ideas for solving multi-agent collaboration and conversion problems. MARL performs well in autonomous cars and the coordination of robot swarms. The summary of our work is the purpose of multi-agent reinforced learning algorithms is to learn an optional policy pi star to get the maximized reward expectations as the equation 1. The scenarios can be divided into 3 areas. First, the fully collaborative scenarios. Agents. Agents need to work together to maximize their global reward expectation as 2, as you can see, as 2. Then, the fully competitive scenarios. Agents need to maximize their own reward expectation and minimize the other agent's reward expectation as 3. Then, finally, the mixed scenarios. The learning of agents policy must consider not only maximize its own reward expectations as 4. The multi-agent challenge is that the multi-agent challenge can be assumed as follows. First, the lack of macro properties caused by the partial observation of the environment. Then, the neglect of others' agents' action. Third, the large giant action space. Then, I'd like to introduce the related work and the preliminary. We divided as follows. We will introduce as follows. First, a reinforced learning algorithm. Then, the problem model. Third, next, the CommNet. And then, the BiC-Net. The reinforced learning algorithm can be divided into 3 areas. First, the value-based reinforced learning algorithms such as deep Q network and the Q-learning. Then the policy-based reinforced learning algorithms such as actor-critic and deep deterministic policy gradient algorithm. Third, the supervising-based reinforced learning algorithms such as Monte Carlo tree search. The problem model, we can describe the problem as the DIC-POMDP, which is decentralized partly observable macro of decision progress. The S-low in S-high describe the state of the current environment. The U in U-high describe the giant action space, and the UA low in U-high describe the single action space. The low A in A-high describe the agent's number, and the P describe the state translation function. The R function describe the global rewards, and the gamma represents the discount factor. O function represents the observation function, and the Q describe the giant action value function, and the R can express as the calculative rewards. The in CommNet algorithm, agents use the fully connection mechanism within a certain range to share the information, using Nj to represent the set of the agents J. The hidden state Hij and the exchange information CJI are used to get the exchange information of the next movement. You can see in the picture. The calculation of Hi and Cij are as equation 5 and equation 6. Then the BiC-net. The BiC-net is the extension of the CommNet, which is based on the bidirectional unstructured policy network to receive the shared observations, return actions for each individual agent, share information about collaborators, and the structure of the bidirectional helps the alternatively increase the number of the agents and the training problems can use by. Then, I'd like to introduce you the Bidirectionally-Coordinated Deep Deterministic Policy Gradient. First, I'd like to introduce the problem of environmental stability. Then, the information sharing mechanism. Third, the large giant action space problem. First, the environmental stability. This work is based on the model DIC-POMDP. At each time step of the training, we can know the action taken by all agents. So, based on this fact, we can assume that the simulation environment satisfies the macro of poverty. Then, the critic net's input data. The critic net's input data is state and every agent's action. We use the RNN structure to ensure every local Q is based on S and agent's actions. The local value function of agent is calculated as the local Q, and then the values are used to calculate the Q total. In the scenario where only a global reward is given, if the sense gives each agent's own local reward, the Q value of each agent can be used to participate in the calculation and fitting. In order to better optimize the state transition function P, we minimize the loss as the equation 5. Then, the information sharing mechanism. Inspired by the work of CollaborateCom to add the bidirectionally structure to the actor network, we can see the action of each agent is based on the partial observation of all agents. This enables the agent to impliedly consider the situation of other agents when making decisions. The equation 7 shows that the hidden state of the agent I at step t in the forward propagation structure depends on this own observation OIT and the hidden state FOI sub 1t calculated by the forward propagation. The backward hidden states calculation is similar to the forward hidden state calculation. The forward output is also calculated by the hidden state. So does the backward output. The final output is a combination of forward output and backward output. Then, the large action space problem. The giant action space in MAIL is large as the number of the agents increases. We adopt the deterministic policy, and the agent's decision is based on their own observations as equation 12. Port action U hat is not an executable giant action. We need to find the discrete action closest to it at Euler distance as 13 equation. Then select the key giant actions closest to U hat as the alternatives, and use the critical network to select the most valuable action and execute it as equation 14. Inspired by the DDPG algorithm, our observation goal is equation 15. Then experiments. We do this on the StarCraft 2 cooperative sensors. In the as you can see at figure 7, shows the partial observation of the agent. The red is our agent, where the red dotted cycle represents the attack range of the agent, and the orange solid cycle represents the operation range of the agent. In the figure 8, shows that n marine sensors, which n is 3, 5, 8, and red is our agent. In these scenarios, the number and types of our agent is equal to those of enemy agent. The purpose of this is to evaluate the willingness to cooperate between our agents. Then the results and the discussion. In 3M scenarios, all algorithms can update their policies on the right direction on increasing the win rate and the rewards. The BiC-DDPG algorithm can achieve the win rate about 60% in the first 1800 epochs. Baseless except the common algorithm seems to find the right updated direction on the gradient. Others Other algorithms are still looking for a better gradient update the direction. The BiC-DDPG can update the policy on a good direction is slightly better than the common and the CommNet, which our algorithm is the red line. The common is the blue line and the CommNet is the green line. The final result of BiC-DDPG shows that they have the ability to coverage the policy learning to a very high win rate in a short-term training time. Then, finally, the trend of the reward curve is like the trend of the win rate curve. In the 5M and 8M scenarios, in 5M experiment, the final results of both Qmix, which is the black line, and the VDN, which is the light blue line, and the BiC-DDPG, which is the red line, are close, and their win rates are stable at 90%. The optimization speeds of the three algorithms are similar, in the range of 50,000 to the 90,000 epochs. The BiC-DDPG obviously spreads the other algorithm. In 8 experiments, the final performance of baseline have decreased significantly relative to the 5M experiment. In 8 scenario, our algorithm win rate suddenly rose to the 90% win rate near the end of the experiment, and the second best performing CommNet, which is the green, was only about 78. So, in the self-contrast, our algorithm performed best in the 5M scenarios, and the final performance in 8M is close to it. Then, the performance in 3M scenarios is obviously not as good as the above two, which proves that the algorithm is not very good at policy learning in a small-scale scenarios. Finally, the conclusion. This paper proposed a deep multi-agent reinforcement learning algorithm, BiC-DDP, which allows for end-to-end learning, decentralized policy on a centralized environment, and the effective use of the additional state information. BiC-DDPG allows the use of the policy-based reinforcement learning algorithm to solve the value-based decision-making problems. Either compared with other multi-agent algorithms, BiC-DDPG improves the problem of the explosion of the decision-space dimension caused by the increase in the number of agents. In the following work, we also intend to modify the effect of the algorithm in collaboration of hunter-gatherers agents in a similar way. Then, we will modify the effectiveness of our agent algorithm in the scenarios of larger number of hunters agents and hunter-gatherers agents. In addition, BiC-DDPG will be deployed in the experimental evaluation of the full-length conversation with StarCraft-2 as a micromanagement model added to the algorithm of the full-length game. Thank you for your attention.
Hello everyone, I'm Bolin from Zhejiang University. Today my report is FocAnnot, patchwise active learning for intensive cell image segmentation. We highlight two keywords to describe our work. That is active learning, which is a special case of machine learning, as a tool for the biomedical task, segmentation of intensive cell images. First, I want to talk about some backgrounds of deep learning. There are a lot of great products or research applying deep learning in many fields. For instance, in autonomous driving, Waymo's of Alphabet, Tesla, Apollo of Baidu. In intelligent assistance, Google, Amazon, Microsoft also have their product. In GANs, AlphaGo is a very famous chess AI. OpenAI 5 and SC2LE are two GANs AIs for Dota and StarCraft 2. Also in biomedical fields, the left picture shows a research published in JAMA 2016. The right picture is a research published in Nature 2017. Both of two works include about 130,000 images to build the awesome model. Such great success can be attributed to some reasons. First of all, many effective network structure and learning algorithms are proposed in recent years. This greatly enhances the generalization ability of model. Then, the emergence of distributed computing clusters, GPU and TPU, improve the computing power to train those deep models. And the most important thing is we have huge amount of high-quality labeled data, which allowed model to fit the correlation. The deep learning model and big data complement each other. However, behind this high-quality data, companies or associations have to spend a lot of resource, such as money, to ask volunteers to collect, pre-process the data. Thus, building a good model will be very expensive. So our general goal is to obtain a good model with limited budget for the task of cell image segmentation. We have two keywords. Accurate model indicates we cannot lose too much model performance in such constraints, and limited budgets means we don't have enough money to label all cell images because doctors are expensive. To this end, there are many alternatives. From the perspective of model, we can adopt few-shot learning to improve model ability. From the perspective of data, we can apply active learning to select more valuable images for the model training. In this paper, we choose the latter one. Now, what is active learning? There are situations in which unlabeled data is abundant, but manually labeling is expensive. Active learning is a learning algorithm can interactively query a user to label new data points with the desired output. Here we have three keywords. Unlabeled data are cell images in our case. Again, labeling by doctors are expensive, and interactively curious means if we have money to label 100 images, we can label 5 images to evaluate how our model works and repeat 20 times. Existing active learning methods usually treat images as a whole during the selection. However, for an intensive cell images that includes similar cell objects, annotating all similar objects would bring duplications of efforts and have little benefit to the segmentation model. Thus, our question is, Is the image level query strategy efficient enough for the intensive cell image segmentation? Here is our approach. There are 6 steps in a selection iteration. In step 1, annotated images are partitioned into patches with fixed size to initialize an encoder-decoder CompNet. For image segmentation, the unannotated candidates with the same patch size are then fed to the trained ED-CompNet. Here, ED-CompNet. To get segmentation results. Here, step 3.2. After that, a clustering method is adopted to cluster candidates into distinct groups. Here, step 3.1. In step 4, we propose a novel query strategy that integrates candidate information at both instance and cluster level, generated in step 3. Based on query results, we select variable regions within images. To expose for the annotation, this is step 5. Finally, these new samples are added to enlarge the annotated data in step 6. The selection procedure is repeated until reaching predefined conditions, such as budgets or money. Before entering the loop, we will partition images into patches. We can see in the original images, biometrical objects, this one, this one, this one. All these ones are similar with partial differences. Image level query leads to duplicate annotation. So we use this strategy to partition original images into overlapped patches. Each patch is considered to be of different importance, so experts are only required to annotate the most valuable regions, some of them, rather than the whole images. In these slides, we show the structure of our ED-CompNet. In step 1, we feed annotated patches for the network training. In step 2, we also feed it but feed unannotated patches for the segmentation or for prediction. In step 3.1, we can get encoder results. We call it patch descriptor for the later clustering. And in step 3.2, we get the decoding results. We call it segmentation mask for the later step 4. Now, we use patchwise clustering in step 3.1. Different regions within an image are evaluated separately to avoid duplicate annotation. We use mini-batch k-means algorithms to improve the query efficiency. On the right side, we show our patchwise k-means algorithm, but we do not put it on our paper because the page limited. After network training and clustering, we have patch descriptor, cluster centroids, and segmentation results. How can we use this information to evaluate so-called worthiness of patches? We propose 4 measurements. 2 are instance level and 2 are cluster level. In each level, we have an uncertainty and a diversity measurement. Due to time constraints, we do not introduce these measurements in detail. Please find how it works in our paper if you are interested. The proposed cluster instance double-ranking query strategy is described in this algorithm. The importance IC of each cluster is calculated and normalized. Recall that we can sum up IC. It will equals 1, which means IC can be treated as a probability of a cluster to provide informative data. For the double-ranking strategy, we use IC to confirm the numbers of required patches in each ranking step. In the first round, we filter out less informative data and retain QC patches from cluster KC based on IU. Corresponding weight score SC of only QC patches are then calculated in the second step. Finally, we pick top TC rankings from refined cluster KC for the annotation. Here is our experimental settings. We use 165 images for the experiments, and we list hyperparameters and metrics used in our experiment. In the table, we list 7 query strategies, including the state-of-the-art method in this scenario, SA for short, and its variant ED-CompNet SA, which replaced FCN in SA by our implemented ED-CompNet, and our proposed measurements. Strategy 1, 2, 3 are baselines using the whole images, while strategies 4 to 7 run a patchwise selection. Especially, the comparison of strategy 1 and 4 investigates the effectiveness of image partitioning based on the traditional RU criterion. For strategies 2 and 3, we do not set contrast tests because SA and ED-CompNet SA both requires n-squared time complexity, which is unacceptable on partitioned patches. In strategy 5, the proposed instance diversity is incorporated with instance uncertainty as a new selection criterion. In addition to the instance level strategy, patches are selected from cluster equally in strategy 6 and proportionately in strategy 7. Note that current strategy 7 is a full implementation of cluster instance double-ranking strategy described in algorithm 1. We do not intend to illustrate each result in detail, but we can see, in a word, our proposed methods outperform the competitors. Moreover, we would like to investigate the model generalization in different parameter settings. The overlapped partitioned approach is always better than the seamless partition. We believe overlapped patches enrich local details of images and provide more variable choice during the selection. Based on the overlapping settings, K equals to 3 is preferred except for true comparison in PA. 3 clusters are enough to describe structures of field objects in this dataset because their contours are less complicated. Too many categories would lead to ambiguous groups instead. The selection of patch size is critical. A small patch size will lose content details and degrade model performance. For instance, L equals to 46 and versus L equals to 128. On the other hand, a large size brings limited benefits to the segmentation as well. Thus, a moderate size L equals to 128 could be a good trade-off to reduce annotation costs with an acceptable accuracy at the same time. In this slide, we visualize the changes in cluster uncertainty and cluster diversity during the selection on average. It proves that the proposed cluster level measurements are effective to help improve the data selection. In this slide, we show the 10 most valuable images selected by SA. Then we mark 10 patches per image in red, which are considered important based on FocAnnot. All these images are from the training set of mix, and the foreign names are their orange IDs of the dataset. Some interesting findings are discussed in the paper. We will not repeat it. So here is our conclusion. The proposed FocAnnot can reduce duplicate annotation and save costs in the intensive cell image segmentation task, which only asks experts to annotate a part of variable regions. The combination of overlapped partitioning, a small number of clusters, and a moderated patch size is suitable for intensive cell images. The last one is FocAnnot is able to reduce additional 15% annotation cost or improve 2% segmentation performance compared to the competitors. Okay, that's all. Thank you.